Thank you very much for coming. As you know, this is NGA-East SSHAC Workshop number 2. A few minutes ago, when I was thinking about this, I was about to say is NGA-East 2 Workshop number 1, but it's not. It's NGA-East 1 Workshop number 2. So as you know, NGA-East is a unique project which has 2 parts, science part and SSHAC part. Under the science, we are developing database, we are developing regions and GMPs and so on, and obviously under this formal SSHAC workshop, we just want to make sure that we are including center body range and so on. On the science part, we really, especially in the last 3-4 months, things are getting together, and we have made real good progress that you are going to hear in the next 2.5 days. The database basically is almost done. The flat file has been distributed internally for QA. We went through redoing and QA and so on repeatedly. You're going to hear more about that. Regionalization with the efforts of USGS researchers now is final. You're going to hear about that one. Validation of the simulation, ground motion simulation has progressed tremendously over the last couple of years, and VS30 at recording sites and other places really is getting together. Is major progress on the science part of NGA-East that you're going to hear more. And now it's the time to get to the formal SSHAC process. We are going to have lots of technical issues in the next 2.5 days, and we really love to get feedback, obviously, from PPRP and others. I'd like to thank sponsors of NGA-East, NRC, that started the whole thing from the day 1, then DOE and EPRI for their support. I'd like to thank really USGS researchers. In the last 2 years, they really cooperated with us on various pieces, especially regionalization and the simulation and other things. And finally, I'd like to thank PPRP. They have been watching what's going on formally and informally in the last couple of years. And I'd like to thank especially TI team and especially Christine and Norm. They have spent tremendous amount of time for preparation of this SSHAC workshop. Thank you again for coming. And now Christine is going to go over the details of the program in the next 2.5 days. Thank you.
Okay, so good morning, everyone. There's going to be a bit of repetition this morning, of course, and, you know, what's the project, what we're trying to achieve, and where we're going with this. But mostly, I think we'll show you the tremendous progress we've made with the project. So the input to seismic hazard analysis comes from 2 major parts, and you guys have seen this figure that's been copied, and that's why it's so ugly. Here we're focused on probabilistic seismic hazard analysis. You need 2 pieces, the seismic source characterization, and this was completed as a SSHAC Level 3 project a couple years ago, and it's the CU-SSSC, that's the source model we use. And then there's a ground motion characterization, and that's NGA-East. We are a ground motion characterization project. So what we mean by East, we refer to CENA all the time. It's Central Eastern North America, so it's this whole yellow area here. So it's basically everything east of the Rockies. So that's what we're looking at. The NGA-East project, as Youssef has mentioned, is a science project with a lot of development tasks in it, and the SSHAC Level 3 project. And our objective is, therefore, again, to develop this ground motion model. We're developing and evaluating GMPs in terms of median ground motion, so GMPs, of course, ground motion prediction equations, and standard deviation to capture the aleatory variability. These are combined together into logic trees to capture the epistemic uncertainty. These terms will come back throughout the workshop. And our mandate is to develop those for ground motions, horizontal ground motions, PSA and PGV. And we're going to talk, especially starting this workshop, we're going to talk always about frequency when we talk about PSA. We still think in terms of periods. Most people are used to that. You'll see why in a second. We want to develop those ground motions from 0.1 to 100 hertz, so 0.01 second to 10 seconds in periods. On hard rock sites has been defined as 3,000 meters per second for future earthquakes in SENA in the range of 4 to 8.2 magnitude. And I wrote MW here as bold M. It's a moment magnitude. Okay, so the NGA-East challenge, developing ground motion model with limited data. So that's what the NGA-West has used, and you can see that in that square box that I stole from Norm, where things usually control the hazard or important and large ground motions. And in NGA-East, we basically have nothing here. These are, I'm pretty sure these are the Gasly records. So, you know, we have issues there, so we need to extrapolate. So that is the challenge. So our critical issues and how we're going to resolve those, hazard critical issues, again, in terms of what we need to characterize for ground motions, regionalization of source and path parameters. And in relation to that, the geometrical spreading in the first 40 kilometers or so, the stress drop or stress parameter, depending if we talk about it in terms of a model, and the extrapolation to ground motions to large magnitude. That's the challenge here. We're addressing standard deviation of ground motions and also quantification of side effects, and for our own purpose, because in NGA-East our goal is to develop ground motions for rock, is to know what the side effects are so we can take them out. So those are the big issues that we're going to talk from different points of view or aspects during the next 3 days. The solution to this is to run a multidisciplinary science project with working groups focused on the research tasks. We'll mention them in a bit. We then build new models, making extensive use of seismological constraints. So that's where simulations come into play. And finally, we do the evaluation and the integration in the SHAC Level 3 process. Most of you are familiar with that, but we'll talk about that a bit. So in our project plan, we have devised M tasks. And in the end, these are our products, right? We're going to end up with median GMPs and standard deviation GMPs, so we call them the sigma models, combined together in a logic tree to capture the epistemic uncertainty. So that's what we're doing here. The thing that is new that you will see is the GMPs that are developed as part of NGA-East right now. We're doing them in a Fourier amplitude space. Norm's going to talk a lot about that. But the whole issue of dealing with kappa and integrating the high-frequency content, if you do it after the fact as an adjustment, doesn't work well. Pegasus spent millions on this, and it's the best way, we think, is to go through Fourier amplitude spectrum. So that's a new thing. So in relation to this median GMP development, we have developed a new RVT group, the Random Vibration Theory Working Group, that's working to help us resolve some issues in there. We'll talk about that. The standard deviation models that Linda will talk about on Wednesday is our idea here is to borrow from what we know from the Western U.S. and then link at small magnitudes and then use that for the East and make adjustments if necessary. So these are our products at the end. The median GMPs will include the new ones we developed, but we're also evaluating the past ones that exist. Okay, so in the task then, we have recorded data sets. Task A, developed the ground motion database. We'll talk about that this afternoon. Then we need simulations to help fill the gap in the recorded data set, as you saw. We have finite fault simulations and stochastic simulations, so we're going to run a lot of runs. Again, this is a simplified work chart or flow chart for our project. There's many subtasks inside of each of these. We felt that there was a need to develop or improve on stochastic simulation methods, and so that's why we have this additional task here, while for the finite fault we only use what is existing at this point. There was a big task on regionalization. Again, it's a critical issue for us, but this is really linked so intimately with source and path studies that now these two tasks are mostly lumped together. So, and all of these feed in as input to the simulations at different places, okay? And we also had a task on reference rock. So what is a reference rock that is going to be used for this project, and also this is completed by the Geotech Working Group and helping us also remove those side effects we talked about before. Yes? Huh? They don't see the slides. Thank you very much. Okay. Do people see the slides now? Sorry, online. It was probably very hard to follow this. The flow is going to come back. Okay, this is what I was talking about. Okay, thank you. So that's the thing when you log in last minute. The final thing we want to address is we want to test the GMPs against other data, like intensity data, to make sure that our final models don't reject any observed data. So this is mostly for paleointensity or intensity data and paleoliquefaction. Finally, throughout the project, we do hazard feedback analysis, and we've been doing that since the beginning to try to understand or to constrain really what is important and what's controlling. So we'll see more on that at Workshop 3. Okay, so where we're at in the project. We've done, somebody removed my desktop sharing. Is it me? Did I do that? I don't know. Okay. Sorry about that. Okay, so where we're at, we've made tremendous project. I kind of say it like you said, like the last few months we've done so much. Anyways, I'm going to stop there. It's starting to flush. But it's true, in the last few months we just converged, and there's just so many tasks that have been completed. So the data set is 98% complete. We shared the flat file with people. We need feedback, but it's going on and it looks good. The reference rock by the Geotech Working Group, this has been completed. It's published in BSSA, and we have reports for that as well. The source and path studies and regionalization, it's completed. It's in publication now, and you'll see those results very soon. Finite fault simulations with the collaboration from a Swiss project and SKEC, we worked like crazy for 2 years, and the validation is done. We started the forward simulations. We're going to continue on that. The development of the stochastic models has been completed, and validation is mostly done. There's one methodology that is not completed, but this is pretty much completed. We started to run forward simulations, and you'll see some of those prelim results. Maybe, I don't know if Norm's going to show them today or not, but okay, we started running that. The standard deviation sigma group, the Western U.S. model is done. We need to adjust with the CNA data, and Linda just got the file last week, so we're looking at that. The epistemic uncertainty of GMPs, the methodology has been completely developed. We need to apply it to CNA. The median GMPs, it's ongoing. We just started really in developing those, and we'll keep you posted. So that's where we're at. We're really at this critical point where a lot of work has been completed, and we can finally build our final products. Of course, the hazard feedback analysis is ongoing. Okay, so what is SHAC? A couple slides on that for those who are not familiar to make sure everybody's on the same page. The motivation came from two PSHA studies conducted in the 80s, and there was a large, of course, uncertainty in seismicity and ground motion, so the two independent projects used multiple experts. What happened with that is they ended up with very large differences in mean hazards, so that was the Lawrence Livermore Lab and EPRI. And looking at that, trying to understand what happened, it was found that the problems were mostly due to procedural issues, like not having the data shared with everybody and not having enough interaction between the experts were the key issues. So from that set of procedural guidelines were developed for seismic hazard analysis, and these are defined by the Senior Seismic Hazard Analysis Committee. That's why we call it SHAC. The implementation is in constant evolution. The level of complexity increases with the number. We're level 3, so we're kind of complex. And the details are all in the published new regs that are available on the NGA-East website. So that's the key there. So what are the goals of the SHAC process? To carry out properly and document completely the activities of evaluation integration. So evaluation is consideration of the complete set of data, models, methods proposed by the larger technical community that are relevant to the hazard analysis. The integration itself, that's what we'll talk a lot about. It's making sure that the models in the end represent the center, body, and range. So if you think of a normal distribution, the median, the sigma, and the tails of the technically defensible interpretation. So the CBR of the TDI, we'll use that a lot, or at least we'll try to think about it in light of the evaluation process. So that's really the essence of SHAC here. Other key features is there are clearly defined roles for our participants. With the agenda, you have received a list of attendees and their specific roles. And these roles then have a specific structured interactions among the participants, especially in such workshops as of today, like the one today. There's a rigorous peer review of the entire process and thorough documentation. So this is true. Okay, so here are some of the key things. We have evaluator experts, so those are to act as impartial and objective assessor of potential applicable models. The integrators, they ensure that the logic tree captures the CBR of the TDI, and these together form the TI team. So Norm Abramson and myself are the co-chair of the TI team. On the TI team, we also have Rob Graves, Linda Alatic, Bob Youngs, and Gail Atkinson. We have resource experts. Many of you in the room and on the phone are resource experts. You have a particular knowledge of a relevant data set, method, or models. Some are specialty contractors, so people were given specific tasks or to run computations and develop products used by the TI team. And there's also proponent experts, so those are the people who advocate for a specific model, be it their own or somebody else's. So many of you are in there, and these people are allowed to interact in this workshop. If you have a RE or PE next to you, next to your name, you're allowed to participate. Then we have the participatory peer review panel. They provide the procedural guidance we talked about, and they make sure the TI team do their job in capturing the CBR of the TDI. So the PPRP, we have Gabe Toro is the chair, we have Rich Lee, we have Jeff Kimball, we have John Ake, and John Adams, who are there to review the work throughout this week and throughout the project. Other defined roles, project sponsors, project leader, Youssef is the project manager, we have hazard feedback analysts, and all the other ones are not listed before, observers, and that's it. In NGA-East, we have additional categories that the Joint Management Committee, so of course Youssef is on there, then we have Larry Salamone representing EPRI, Stephen McDuffie representing DOE, as well as Cliff Munson representing the NRC. Those three are our main funders. So we have a bunch of working groups, so the different research and proponent experts are grouped into a database working group, geotechnical working group, GMP working group, the random vibration theory working group, the Sigma working group, simulations, and finally source and path studies. Dave, I have a nice seat for you so you can hear. We just got two people coming in late, so TI team member Gail and Dave Poor. Okay, so again, lots of progress in the last few months. Finalized the database, finalized regionalization of ground motions, completed the finite fault validation, published reference rock and kappa, that's the geotech working group did that, numerous publications on many subtasks, and created and engaged a new RVT working group. And we initiated new regression models in 4 amplitude space. So this is here the SHAC process flow chart. It's pretty complex, but the key here is that we're at workshop 2. That means that we've collected most of our data, and we now have resource experts and proponent experts to review the work and alternative models. That's when we finalize the database. The next key steps for us is to come up with our models and do more hazard calcs and sensitivity analysis that we'll present in workshop 3. So I'll bring you the schedule in a second. We're on track, and here's the schedule. We're here in July 2014, workshop 2. Workshop 3A is October 29th, 30th. Okay, so that's when we'll start to show the logic trees a little bit more and have more proponent discussions than today, further proponent discussions. Then we have a workshop 3B because we anticipate we need a quick turnaround and feedback from the PPRP on this in January 21st and 22nd. And we have a project wrap-up April 13th for the project reveal final products. Throughout, we'll finalize the documentation and have numerous exchanges with the PPRP as we move along. Okay, so today we're at workshop 2. This is defined in the SHAC process. I'm sorry, it's very wordy and tedious, but we have to go through this. We're to review critical issues and data needs and proponent discussions. So we still, well, if we haven't identified the critical issues at this point, we're cooked. They have been identified. We're solving the problems at this point. So we're going to present, discuss, and debate alternative viewpoints. We're going to identify the technical basis for the alternative hypothesis and discuss the associated uncertainties. And we need to provide a basis for the development of hazard models that we're going to come up with in October. So this is not a typical research meeting. We're not going into details, and we're not excited about that little point that's an outlier there, and we're going to try to go through this and really focus on the objectives of the SHAC workshop. The presenters are all going to show products and results from collective work. So it's not just one person presenting their work. The discussions are then focused on the critical issues. We will have proponent discussions when appropriate, mostly Wednesday morning. The interactions are structured. If you're not a resource expert or a proponent expert, you're not allowed to talk until the end of the day. You're considered an observer. But if you have a good point and you think we have forgotten, let Norm or myself know, and we can bring those issues up. Okay, at the end of the day, we left some time for the observers. This workshop, as all of our workshops, is all recorded and it's going to be put online. So for that, we ask that all the participants on site need to use a microphone. And if I just yell microphone, need to wait for it. We have two great helpers. Our project, we always have overqualified helpers here. We have Sifat and Sahar, both graduated students, who will help with the presentation, running the show, and doing all that. If you're a presenter, make sure you give your slides to them. They're going to also help with the microphones as we go along, okay? So when you take the mic, say your name, and then go with your comments. So the remote attendees, you can raise your hand. Some of you have already been raising your hand and asking questions to Sifat, or you can send an email to Sifat Mouin. Our email is in the invite that I sent you last week, and then we can resolve those issues there. The agenda and additional information is available on the Peer website. Okay, so there's one thing that I want you guys to think about throughout this. Let's all be alert. And a small note on cognitive bias. We are here to discuss, but we want things to remain objective. So there are large uncertainties in understanding and in models, right? We don't have a lot of empirical data to constrain that. So this means we need to have expert judgments, and if there's an expert judgment, it means there's a potential for cognitive bias, okay? So we can be overconfident that, focusing only on what we know. For example, hey, my model works great at magnitude 4, but what does it do at 8, right? So that's an example. Availability, giving too much weight to a certain data set or a recent extreme event, and mineral suddenly controls everything, or something like that. Anchoring, so focusing on models that have worked in the past. We're evaluating everything as of today, including past and new models. And then, ignoring conditioning events. So I guess it would be more for a proponent modeler, not really stating the underlying assumptions that are implied by the model. So the most effective solution to dealing with cognitive bias is to be aware of it and to ask the right questions. So all the speakers were sent questions by the TI team of points they needed to address, and again, we're all here and we're going to refocus and ask questions as needed. So agenda in a nutshell, you have it printed out, but today, this morning, we'll talk after this, what Bob Young refers to as the fluff. After the fluff, we'll go into GMPs and the development of NGA-East GMPs. This afternoon, we'll talk about the database and the regionalization and sorts and path studies. Tuesday, tomorrow morning, we focus the whole morning on epistemic uncertainty, and we'll need the whole morning, believe me. The afternoon, we're going to talk about simulations. And finally, Wednesday morning, we're going to talk about GMPs again, but now in talking more about proponent models, and also go over the standard deviations model. Okay. So in the interest of time, I'm just going to flash through here, and I'm just decided I'm not going to present this. But I have put online for everybody the nomenclature of residuals that comes from Linda Alatic paper et al. From 2010. And this is something you should review, and we'll refer constantly to between event residuals and within event residuals and site-to-site residuals. And so I made a PDF that's available on the website. And so if you're not fluent into this language, please review that, and you can print it out or look at it online. And this is going to come back throughout. So it's only 2 pages. It's a short PDF, but I ask you all to make sure to review that. Okay. So I think we're ready for Norm.
Good morning. So part of this project is developing new sets of ground motion models as opposed to just evaluating the existing sets of ground motion models. And that's the part that we assigned to the peer NGA project. And we wanted, so the approach that we're going to use is described here. Christine alluded to this, is that we are switching from the traditional approach of trying to model response spectral values and develop a model of how the response spectra behave based on magnitude and distance, for example, in site condition, to starting with a Fourier amplitude spectrum model. And there's a couple reasons for that change. One was trying to deal with kappa. So Christine mentioned this a little bit. Building kappa into a response spectrum model empirically is just about impossible. So Linda and I tried as hard as we could to put it into the NGA West 2 model and gave up. Okay, so and the basic problem is response spectra amplification factors at high frequency depend on the spectral content. If there's no high frequency energy, you start to sample back to lower and lower frequencies. That's what the response spectrum does, and it's just a very difficult thing to work with. So instead, what we're going to do is develop a model first for the Fourier amplitude spectrum. This also has the advantage that it allows us to tie much better into the seismological models as opposed to trying to get the seismologist to work with response spectra. We can repeat over and over what the difference is, but as soon as you say spectra, a seismologist thinks Fourier spectrum. You just cannot get that out of their thinking. That's what they're taught. The same as when we talk about spectra to engineers, they're thinking a response spectrum no matter how many times you say Fourier spectrum. So we're going to try to be really clear in these next 3 days which spectra we're talking about. But most of what I'll be going through here is all on Fourier spectra. So we're going to develop a model of the Fourier spectrum. This, again, allows us to use seismological constraints, easy to incorporate kappa effect. The site response also becomes a whole lot easier when dealing with kappa. Okay, site response as well, when we're trying to do amplifications and spectral values, was having a very difficult time in the effect of nonlinearity and so forth on the kappa effect. it becomes really easy, actually, in Fourier spectra. So then once we have those models, we have to do something to turn them into response spectra, because that's what we have to provide to the engineers. So we'll run a suite of forward realizations of our Fourier spectrum model. The key of this is that the extrapolation outside the data range is being done in the Fourier spectra space based on that model, and we're going to be able then to create a well-behaved set of response spectra, a huge number of magnitudes and distances and kappa values and so forth. At that point, the curve fitting is really easy, right? It's all interpolation. There's no extrapolation, and we'll have plenty of data to be able to do it. You could even just do a non-parametric equation at that time and be done with it. So that makes it easy. Okay, so we're going to have our forward realizations, then we have to convert those to response spectra with RVT. That's part of the tasks going on, is the calibration of the RVT models to make sure that they're working properly. How do you get the duration that works with RVT as opposed to the duration that corresponds to some particular Aries intensity number, for example. And then we'll develop our GMPEs, okay? And I said here, the key is we don't extrapolate our curve fitting in the response spectral space. That's all going to be done on just interpolations, because we have plenty of numbers. So there's three approaches that we're going to be using. Okay, one is an empirical approach with seismological constraints. So this is not assuming any preconceived spectral shape. We're just going to fit the Fourier spectra, dependence on magnitude and distance and site condition, like what we do for response spectra. Okay? We'll also need to use finite fault simulations, though, to help us, because as you saw from Christine's slide, we are woefully missing data where we care about it for fitting. Okay? Then we're going to, another approach is using a point source-based model for the Fourier spectrum. So with that, you have an underlying frequency or shape that you expect the model to fit with, and you can use that. Okay? So it will fit all the frequencies at once, as opposed to fitting the frequencies one at a time. So when we're running the empirical model, we're going to again do regression for Fourier spectrum. We want to make sure that these things are all matching together. So this may seem like a little detail for you, but this will explain why we're having several of the talks that are following here. So when we do a regression for Fourier spectrum, we need to have a statistical model of the distribution. We fit the median Fourier amplitude spectrum. So we're going to fit it on log space. We're going to fit the logs of it, and we're going to assume it's log normally distributed. Okay? Again, no assumption on what the shape is for small magnitudes, seismological models, or finite fault simulations to help us constrain how things should scale up to large magnitudes. The standard deviation from this regression is important to us. And the reason is, for RVT, we need to know the mean Fourier amplitude squared values, right? So we can compute the RMS accelerations and so forth. Okay? The regression is going to give you the medians of the amplitude. We want the mean amplitude squared. So if you know the distribution, you can do that. So we'll have a standard deviation shown here, sigma regression squared. That's just what comes out of fitting our median values. That's we're assuming log normal. And then we're going to have a standard deviation of what the individual frequencies we're doing within the bandwidth over which we're smoothing. So we're not going to be fitting 10,000 frequencies. We're going to downsample it to a smaller range and smooth over that range. But that variability needs to be brought back along so we know how to compute the right mean value for the amplitude square. Okay? That's just for using it for RVT. That's not the numbers that we're going to be propagating directly into a I didn't touch anything. Okay, all right. And now I'm completely lost. What was I talking about? Oh, not the sigma of the response spectral values. We need to get that from fitting response spectral data or bringing those numbers in along from global studies, for example, or transferring the western sigmas. This is solely to get us the right value that we can put the spectrum into the RVT calculation and get everything to work out in a consistent way. So RVT has a couple pieces to it. There's a peak factor model that's been selected by the RVT working group and is being used for all of the approaches, so we at least are consistent in that number. There's a duration model. We need a duration model that works with our Fourier spectrum model and our data. And Nico's going to talk about an example of how that's been done on some other studies, but we need to be able to then pull out a duration model. This duration model might not be the same between the different approaches. It's a duration that makes the RVT work with this characterization of the Fourier spectrum. Okay? The duration model also has to have a way to extrapolate it to the cases that we care about, back to the big magnitudes. So one of the problems is going to be we can calibrate the duration for the available data set. How do you make that work where we want to apply it? So it's going to have to bring some other source or path concepts of scaling of duration into it so that we can get a magnitude 6 or magnitude 7 duration out of that. And then we develop our ground motion model. And that bottom part is going to be basically the same for all of the approaches. It's easy at that point because we have a well-behaved data set. The other approach is to use SM-SIM modeling the median ground motion. Okay? So this is the work that Dave Bohr is doing right now, and they're looking at available correlated sets of point source model parameters. Remember, we've talked many times, you can't go pick parameters from different studies. You need a set that works together. Okay? The model itself is producing not a median Fourier amplitude spectrum like the previous regression, but it is producing the mean, the square root of the mean value of the FAS squared. That's the thing that fits with the RVT already. So there's no need for tracking the standard deviation of the Fourier amplitude spectrum because the model is giving you the right number that already goes into RVT. Okay? So the reason for talking about this is we need these different approaches to fit together and to be trying to estimate the same parameter. So we have the same peak factor model because they need RVT in this approach. There'll also be a calibrated duration model that works with this point source model, and Dave Bohr is going to talk about that later this morning. Again, this duration model is already, though, parameterized into source and path, and so it is already set in a form that will extrapolate to larger magnitudes. And the GMP development is the same. As an alternative to that, Walt Silva is going to be developing a model, point source model for the median based on a regression of the Fourier amplitude spectra. So this is fitting the point source parameters to the data set that we have. Okay? So it's a broadband inversion of the data, not frequency by frequency, okay, as we're doing in the first part. For this, because it's fitting data and he's going to assume log normal again, he's getting a median spectrum out, we need to keep track of the standard deviation of those pieces in the same way so that we can get back to the mean value of FAS squared. Okay? So for the first and the third approaches, we need those sigmas to be able to tell the difference between a median and a mean value. Okay? And the RVT will be using the same peak factor models. Probably we'll need a new duration model. It's not sure, so Walt's going to look at either existing or new models, again relating it to how the source scaling has to work. Okay? So that's what we're doing to develop our new NGA-East GMPEs. So I can show you now some preliminary results that have been done. This is by Justin. Wave your hand, Justin. So Justin's been doing all the work. I will take the credit as all good. As we get older and older, that's what you do, right? Take credit for younger people's work. So Justin, so we're going to talk about a preliminary fit to the Fourier amplitude spectrum, okay, using a model that is really simple, right? It actually is. So we just have a simple quadratic term in magnitude. We've got a slope on a geometrical spreading, a Q term out here, and a VS30 term. About as simple as you can make this thing. It's broken up into two ranges, a geometrical spreading that applies before a hinge distance, and a geometrical spreading then applies later. So we're going to talk about coefficient C4, the geometrical spreading in the short distances. C4a is the change in the geometrical spreading term, okay? So if C4a was 0, then the geometrical spreading beyond this hinge distance is the same, okay? If it's positive, then it's getting less geometrical spreading. If it's negative, it's getting steeper, okay? Just so you know what those numbers are. All right, well, so we'll go through a bit of what these terms are, what it look like. So first, geometrical spreading. So there's an initial regressions that have been done with the data sets, and the thing that becomes important is what do you use for fictitious depth? Okay, so we all know back here, we've got a term here, in this case it's a hypocentral distance. We're using that because that's in the data set now. We'll probably go to a rupture distance that allows a smooth transition to larger magnitudes. But for the events we have, this is okay. Fictitious depth is this C6 term, right? We've always had that in our GMPEs. We know we need that. We've seen it on Western data over and over. As you get close into big earthquakes, there's the attenuation curves all bend over, okay? But how do you model that from the kind of data that's available for this study? Okay, what is the distance where that breakpoint is in the geometrical spreading, and some plots of the uncertainty in those terms. So this plot here is the fictitious depth models that were in the NGA-West 2 models, other than the joiner, or excuse me, the BSSA models, which uses joiner bore distance, so it doesn't. The term doesn't have the same meaning as it does relative to a hypocentral distance for small earthquakes. Some of the models here have a constant term, 8 or 10. The Cho and Young's model has a strong increase. That's also related to the way it's doing its saturation terms. And then the ASK model down here has a very low geometrical or fictitious depths for small magnitudes and increasing. This is important in terms of how you fit the close-in data from small magnitudes. These other terms up here really are calibrated from larger magnitudes and don't work so well when you get in close to small earthquakes. Okay. So as an example, though, what happened? So Justin ran a regression at 5 hertz. So on these axes here, this is hypocentral distance, and I wrote it a little bigger, 10, 100, and 1,000 kilometers. This is for amplitude spectra here. That's 1 decade. You'll see a whole bunch of plots like this. The fictitious depth term, if we just allow the regression to pick it up, is the red curve. Okay, and you can say, why is it doing that? It doesn't work. You know, it's missing all of this other stuff. The red curve, the regression is trying to fit the data the best it can to minimize the variance. Most of the data are at larger distances, so it's making changes to the fictitious depth to try to get a tiny increase or improvement to the fit here, which actually has more influence on the variance of the fit because there's so many more data points there. If instead we use fictitious depth scaling in the ASK model, okay, that goes down to a small value, then you start to get the curve that you see from the blue one. And here we're doing a better job fitting the sparse but data that are available there at short distances. Okay, so this is going to be an important part for us. We cannot derive or estimate the fictitious depth term from these data. It has to come from somewhere else. In the rest of this, I'm going to show it relative to assumed fictitious depth using the ASK model. If we look at different places for putting the break and the hinge point, so this has been around in Eastern U.S. models for a long, long time, right? It's nothing new, but we looked at break points in the geometrical spreading at 40, 70, and 100 kilometers, and what does that do? Okay, so you can see here, this is the break at 40, the break at 70, and the break at 100. in here, they're all fairly similar fits to the data. There's some differences going out. We do get differences, though, in close. Remember, in close is what we're going to care about when we try to drive hazard down to 10 to the minus 6, right? You're going to pull things in. All right, I'll show you as well what the residuals are looking like in close. So from this model already, you can see in close the hinge point of 40 kilometers is closer to an average in here, whereas the hinge point out at 100 is systematically underestimating the short distance data. If we look at what that geometrical spreading coefficient looks like using a hinge of 40, okay, which is going to be what we're using right now moving forward, because that looks to be the best for trying to recover the short distance attenuation. On the blues are the C4 term. Okay, so they're sitting, this is -1, that's -2, so this is right around a -1.2 value. It goes up and down, but that's the kind of a number that we're seeing. Similar to the values that we've been seeing before, up to 1.3 I think Gail has been using, and 1.3 would be a little bit near the bottom of this range here. 1.0 would be there. Okay. The C4A, or the change in that coefficient as you move across the hinge point, is shown by the red line. So this is about, from here to about a value of, say, 0.5 to 1. So if we had a -1.2, we would be looking at numbers between -0.7 and -0.2 if it got all the way up to 1. Okay? So this is controlling how that scaling goes. This term is going to trade off with your anelastic attenuation term. We call it the gamma term, the one that scales on linear R. So there's a really high correlation in what those are. Okay. If we look at the within residuals close to our site here, within 10 kilometers and within 20 kilometers, you can see what we're getting, even using, this is as a function of frequency now for each of the frequencies. The red ones are our residuals within 20 kilometers, and we're centered on 0, so we're doing an okay job there. The blue ones are within 10, so there's a lot less data in this range, but we're overestimating the ground motion by about 10%. This is a, I'm sorry, this shouldn't be a 1 and a 0, that was my fault. This is a -0.2 and a +0.2 here. So this is about a 10% change, whereas we're about centered on 0 for 20. So this is still saying this isn't quite centered right on these data. I still think we're going to have to, though, go look at other data sets that are more rich in the short distance scaling to constrain that term. If we look at the uncertainty that comes from this, so here Justin just did a randomization of the coefficients that come out of the regression using the covariance matrix that comes out from the coefficients. So each one has uncertainty, but they're correlated with each other. And if you randomly sample that, this is it 50 times or 100 realizations? So this is 100 sort of this is our statistical error in what the fit could be to these data. And so you're seeing what the range is here, about 30% where you have data, and then it grows, of course, when you're near the extrapolating to the large or small distances here. Okay. So that's going to be part of how we can go to our epistemic uncertainty. What's the underlying simply statistical uncertainty in what the fit is? If you look at the magnitude scaling that's coming out of this, this is, again, the same thing at 30 kilometers. What's the uncertainty in the magnitude scaling? Just from the statistical fitting of the data. Okay, so it's a pretty simple magnitude scaling that comes out of this, controlled basically by a linear term. And this is out at 200 kilometers. Our interest will be out here at excuse me, if I go back, does this thing bend over? We need, if we were looking at Western U.S. models, there would be curvature here, and this thing would start to flatten out as I go to high magnitude. We have breaks in our scaling at around 5.5, and then we have another break at about 6.5 in the Western U.S. models. So these data aren't sufficient to pick up those breaks in the scaling. We have to use some other information, numerical simulations or understanding of how things scale in the Western U.S. to control that. So the other part is site terms. So one of the effects we did on the regression is These data sets are now rich enough, especially with the TA array data, that you have multiple recordings at sites. So we can actually start to get out site terms from this. Okay? So if we look at what is the within event standard deviations, okay, shown here, there are 3 terms that we're going to talk about. The phi term, this is our standard ergodic one, shown by the black points. The phi S2S, that's the standard deviation of the site term. The site term is now a site-specific estimate of how the data at that site differ from what you expect just using VS30 scaling. Okay, so we fit VS30 scaling. There's a dependence in there. I go and I say, well, this site, this particular site, I've classified it as 500 meters per second, but it is systematically high at 1 hertz, and it's systematically low at 5 hertz. Okay? So with that, we can start to figure it out. Linda.
This is Linda. Okay, is this this is the Fourier fit?
Yes, this isn't response spectra. Okay. This is so everything here is Fourier spectra. You won't see response spectra from me for another 6 months, okay, until we're done with the response spectra. 4 months, Christine told me. 3 months. It's getting shorter. Today, in these presentations, it's all Fourier spectra. So these differences, you can't just correlate them, Linda, with what you had on response spectra, because it depends on the frequency, smoothing, the bandwidth, and a lot of other things. But we can see relative what's happening. So the phi S2S is the blue ones, is how much we have a variability from site to site at a given frequency. Okay. Once you've corrected for VS30, what's left? Okay. The red is our phi SS, so that's our single station within event standard deviation. Okay, so that's going to the regression and saying, let me take out the site terms. What's left? And you see a very large reduction here, numbers from, say, 0.75 down to about 0.5. So we have a very large site term. What's the cause of that? Okay, so part of the cause of that site term is misclassified sites. And that's going to be part of our issue here, is that we don't have a really great, robust site classification. A lot of these are based on proxies or some other way to estimate it. Okay. If we go to look at what the shape could look like in the scaling, this is an example of the VS30 factors in log space and the kind of a shape you would expect. I think this was for a 500 meter per second site compared to a hard rock site with flat. So I got a term here that's going to give me an amplification, or terms that look like this. And what you want to do is to say, so when these are the same as looking at what's in, how we're scaling VS30 in California models. The key is there's a shape here to this that we're trying to take out of the data. So we think that shape is in there. This is what we can see systematically. But now let's go look at data. This is an example of the frequency dependence of the site term. So when we say site term, it is not the coefficient on VS30. The site term is the deviation of the average response at that site from your VS30 scaling. Okay, so let's be sure we know what we're talking about in terms of terminology. Often we refer to a site response term or something as the slope on the VS30 scaling. That's not what's here. This is showing you the difference. If I had a site that was following the VS30 scaling in the model, then my site terms are near 0. So this is a site here, these two, where it's pretty good. Meaning this site is consistent with other sites that have been classified as at VS30. Doesn't mean it's absolutely right, because this is all relative, but these are consistent. If I look at this site, you see there's a big, strong shape here. Okay, that's going over 1, so we're looking at a factor of 3 difference. Remember from the previous slide, we have this kind of a shape, and this is now sort of the inverse of that. This was classified as a hard rock site, and it looks like it's not a hard rock site. So we're able to use these site conditions here, our site terms as we move along, to try to figure out which sites are reliable and which ones are more questionable. What's important of this is that we're going to be taking the site terms out in the regression. Once you take them out, you really don't care what the site was, other than for nonlinear effects, but for just a standard model, that's not important to us. But we need to know later on, after I fit this regression, where is it centered? And how do I adjust it to my goal of getting 3,000 meter per second hard rock site? So that's going to be our charge or our difficulty, and we're going to be able to use some of these to tell us which ones are reliable and which ones aren't. I think we'll end up trying to get a regression relative to the more reliable site conditions, or at least internally consistent site conditions. So that will be part of the issue that we have to face. But we're now being able to see impacts of potentially misclassified sites, and it has a big effect. This doesn't just happen in the East. Similar things we're seeing in the NGA data set. Brian chose going through this type of a plot for the suite of models from the NGA West 2, and you'll see some sites popping out with a really strong signature indicating or suggesting we just got them classified wrong when their site response looks just like the VS30 scaling said it should, or for a different VS value. The other issue we have in all this is correlation. Okay, this is the nemesis of ground motion data evaluations. How do you deal with correlation? And what's shown here is the site term, and then on the shown by the points here, as a function of the mean hypocentral distance. I said depth, that should be distance, excuse me. So if a site has a mean distance of 800 or 1,000 kilometers, it means it's only showing up really at large distances. So now I have to fit the distance dependence, right? And so the site term and the distance dependence become correlated and locked together. So this is going to be another key issue for us. How do we avoid this? So part of the early regressions that Justin had did, we were seeing no difference in attenuation regionally, partly because the site conditions were soaking up the differences in the regional attenuation, because that site was always recorded at large distances. So if it should have been a steeper attenuation, you just put in a negative site term and it thinks it's all the same. So that correlation is going to be a real problem for us that we're going to have to address. We can't simply throw all the data in there. We're going to need to use subsets of the data where there is a range of distances over which the site was recorded. If you don't do that, you're just trading things off again. So the next part was regionalization. And I'll show, so there's the regions that we've been talking about: Gulf Coast, paths crossing from the Gulf Coast, Mid-Continent, the main region there, Appalachians, Atlantic Coastal Plain, and then other crossing paths that don't involve the Gulf Coast. So I'll show you a series of plots like this. We've got the attenuation for the different cases, and the data points have all been renormalized to a single magnitude 4.5 so that we can plot them on top of each other. And you can see the differences in what the fits are for the different values. The Gulf Coast are down here, steeper as expected. The other regions are up on the top. If we simply go through quickly and say, here's the Gulf Coast data, you can see where the data are available. This is paths where the earthquake was located in the Gulf Coast and the site is located in the Gulf Coast. Okay? So this is the one that's fitting the lower path, and these are the available data. Not a lot out at large distances to work with. This is the Gulf Coast crossing paths. There's a whole bunch of those going up towards the north, and so that controls that part of the shape. If you look at the Mid-Continent region, there's a lot of data here, and this is now following this more central model up here. If we look at the Appalachians, we have some data still to work with, but it's sparser and mostly out at the larger distances. And then if we look at the Atlantic Coastal Plain, we're running out of data. So that's a real problem in terms of you cannot empirically get at what is the distance attenuation. If we look at crossing paths, these are all paths crossing other than through the Gulf Coast, we see what the attenuation is. All of this is leading to factors of probably 3 or 4 in the Fourier amplitude spectrum here at the high frequencies. Okay, the other part is if we look at the event terms, if you can see these, so this is versus magnitude. We do have a couple outlier events down here with some very low residuals, but the model is fitting adequately the event terms as a function of magnitude, because then we wanted to see how do these scale with hypocentral depth. One of our key issues is stress drop and its dependence on hypocentral depth. Is it constant or not? These data here are basically flat with hypocentral depth, indicating we don't see a scaling. If you believe all of this and don't worry about all the other correlations that could happen, you could conclude no depth dependence of stress drop is needed. Rob.
Okay. Rob Graves, just a quick question. For this plot, are you able to split these in those regions as well to look to see if there's any regional dependence for the event terms?
Yes. Hasn't been done yet. But yes, there's a bunch there. I'm more worried, though, Rob, about fundamentally the correlations that are going to happen here. For example, does magnitude and depth correlate so that we suck up the depth dependence with magnitude scaling? There's other things that we just have to be really careful about before we jump to any conclusion. In the West, in the NGA West 2 models, we found strong scaling with depth. So why don't we see it here? You'll see some discussions on stress drops where some of the data indicate there is a depth dependence, other data indicate there's not a need for a depth dependence. But from this analysis, with all the limitations of correlation, okay, which can be really misleading, I want to warn you about running off and saying, there's no depth dependence to stress drop here. We don't see it, but we may be accounting for it in a different way in what's going on. Okay, so our empirical data sets are finally, happy days, ready to use for generating the empirical GMPEs for Fourier amplitude spectrum. Okay, we need to bring in the results from the finite fault simulations to constrain the large magnitude scaling. Right now, all we're fitting really are these basic things of geometrical spreading, site conditions, and so forth that are in there. The geometrical spreading looks to be about minus 1.2 in the first 40 kilometers on average, probably plus or minus 0.1 that you could bring along there. Reliable site classifications is a big problem for us. Okay, so we're correcting the data, but in the end, we're looking at using these site-specific site terms such that my answer is not sensitive to the VS30 estimate. However, we have to be able in the end to correct whatever the empirical model is for Fourier spectrum to a reference hard rock condition. So I have to know where is the whole thing centered. And the other part of this, I didn't write down here, this whole issue of correlation that is the thing that keeps rearing its ugly head over and over and over. Okay, you can get residuals that look great, and your model is making no sense. Okay, so that you have to have some other constraints brought along the way so it makes physical sense. The regionalization is going to be difficult to resolve other than the Gulf Coast using the available ground motion data. Okay, so there just isn't enough. We're going to have other data sets, simulations or intensities or whatever we can that may be broader spatial or better sets of recordings to see if our regionalization makes sense, okay, and how we can do that. It looks like actually there's some pretty simple rules for crossing paths. They're not jumping tremendously, so we're not going to have to develop a really complicated scheme for how you calculate the ground motion crossing paths, so that's good. And in the depth-dependent stress drop, we don't see it in the event terms, but we've got to worry about correlation between depth and other terms that might be absorbing that effect. It is so strong in the data that we see in the western United States, it's a big jump to suddenly say none of that is seen in the eastern United States. And that's it for our summary. Ralph. He needs the microphone.
So Norm, two questions. One of them is, you know, if you're going to be using the Fourier amplitude spectrum, it's going to be critical then that you provide guidance, at least to those of us who are doing simulations, as to how you're averaging the Fourier amplitude spectrum. Because for a particular frequency, like if you're at 5 hertz, you're going to want to average, some bandwidth around there. You're not just going to select that point, and that's going to be very important to us to know, because the other thing, part of that is that the Fourier amplitude, when you're doing the averaging over the number of points, that number of points depends upon the duration which you selected to do the FFT, because delta F is equal to 1 over T. So the number of points that you're doing in the averaging is also going to depend upon that duration.
Yeah. So what you're getting at are the advantages of a response spectrum, because it does all that for you. Okay, but yes, so we have those things defined in terms of what are the bandwidths that we're going to be using. We've been taking all of the empirical data and padding it out so we get the same step size and frequency. Okay, and we're tracking the standard deviations within our smoothing bins so that we can add that back in. We need that piece for the RVT calculation. But you're right, we need to the simulations have to be doing the same thing with their Fourier spectrum.
Thanks. The second question I have is that in your initial model, that regression that you had hypocentral depth plus you had that C6 term. Okay, but the hypocentral depth already has a depth in it, right? Yeah. So what is C6? Are you adding to the depth of the?
Yeah. So when we say fictitious depth, this is a term that is generally makes up for approximating a finite source by a point. Okay, so that can be thought of not depth term, but think like if I have a magnitude 7 earthquake, this could be a distance along strike term. But we call it fictitious depth as in tradition, but it's just a way to say the energy is not coming from the closest point, but is coming from a point somewhere else on the rupture plane that's a little bit further away. So that's what it's for. So as you go to small earthquakes, that should go to 0, right?
Right.
Okay, so that's really, in the model that I had done on, in the ASK model, we drove that down to, I think, 1 kilometer or something, just so that it wouldn't be getting zeros. Okay. But you're right, that needs to go to small numbers for small earthquakes, or it doesn't make sense.
Okay.
The other models that kept it large really were models intended to work at large magnitudes, and they just didn't care about missing small magnitudes at short distances. If that had been the focus, a different model would have been derived.
Well, I think we're going to keep the questions for after, because we're going to have tons of discussions to have. So are you okay with that?
I'm okay with that.
Okay, so that's what we had on the schedule. We'll just go through, keep your questions. Some of them will be answered in the next few presentations. Did you finish your slide?
Yeah, I think we should try to have some questions, but limit them to a few minutes, right? Otherwise, it's too hard to sit and listen and
Absolutely.
not say anything. All right.
So, Walter, you look antsy. You wanted to? Walter Mooney.
Yeah, Norm, I'm a seismologist, and it took me forever to figure out the difference between Fourier amplitude and response spectra, So now we've done the regionalization with the response spectra. And now you're switching on me again. So are we going to have to redo the regionalization with Fourier spectra?
No, I guess we're not going to do it for this project. Part of the reason for that is we want the regionalization to be relevant to response spectra. So if it doesn't matter in the response vector, then we can say we're going to skip it. I think in the context of how we're doing things, we probably in the long term will want to look at all of that in Fourier spectra so that it's consistent. And I think it'll be easier then to integrate the seismology with these kinds of empirical models by working in Fourier spectra. So I think it's a step forward, but for what you guys provided, it's informative in terms of how we want to use it, and it will be used. So once we see it's important for response spectra, then we will bring that along in our regionalization, the Fourier spectrum part, and then we convert it back to response spectrum at the end.
Yeah, so the end product, we're still producing PSA models. They're going to be used as PSA in the end. So that's still consistent. So do we have, the reason I'm rushing everyone is to make sure we can get Olga on the line. Everything's working and she's in France. So if you can, Olga, are you there? Can you hear me? Thank you so much for joining us.
Okay, thanks for the patience with getting the line straight. So hi from Greece, everybody. And this will be about kappa and related issues. So this is just a list of the questions I received that I should cover. I've changed the order a little bit, but hopefully it should all be in here. So to begin with, what is kappa? It's the deviation of the acceleration spectrum at high frequencies from what it should be with according to theoretical models such as the Brun. So kappa is what brings this guy down here in actual recordings. And the way we want to try and treat it in the project in terms of computing it, we can think of it this way. So with respect to the corner frequency, we have two different approaches. One is looking at the entire band of frequencies. So I'm kind of showing this here, and that's the broadband approach. And then so this includes the corner frequency. And then if we exclude the corner frequency, we either work above it. For example, the first sketch shows you the Anderson-Hoff method, which we're going to be calling the acceleration spectrum. So there you work on the acceleration spectrum above the corner. Or you can also work on the displacement spectrum beneath the corner. So the idea is you need to work where the spectrum should theoretically be flat in order to be able to see some sort of a decay with respect to the model. So the broadband approach, that will be, well, that's the Anderson-Humphrey and the Walt-Silver approach, and within the project it will be done by Walt and Bob, so PEA. And I'll just say that the idea is to fit the entire spectrum to the point source stochastic model, and they get out a bunch of parameters, which may include stress drop, kappa, frequency dependent Q model, and also it accounts for crosstalk amplification, and I'm going to come back to the amplification issue in just a bit. And with respect to the two approaches that we're going to use that exclude the corner frequency, the Anderson-Hoff method, we're going to use it for the larger events where the corner is pretty low, and then the displacement spectrum, otherwise called the mini kappa approach, we're going to use that for the smaller events where the corners are rather high. And be it as it may, whichever of the two latter methods we use, what we're going to be computing is, for example, one of the points here, which means that we're going to be measuring a total kappa. And the idea is to try to separate, well, to take away the path contribution, so what's mainly due to the crosstalk Q, which I'm drawing here in, which I'm marking here in blue, from what I'm marking here in red, which is the site-specific kappa, which we'll be calling kappa 0, and what we'll be using is the kappa 0. So the details I'm going to give you mainly pertain to the two latter approaches, so the approaches that exclude the corner frequency. And the procedure, as we set it out with Norm and the rest of the people, starts by setting objective criteria in order to select the frequency band in which we can work. And this is just a visual aid to show that. So we have our S windows and our noise windows, and this is just a sketch of two spectra for noise and S waves. And the first thing we need to keep in mind comes from the NGA SSHAC file. So it's the lowest and highest usable frequencies, which may be affected by the Nyquist, the instrument gain, and any filtering done. And we especially care about the highest usable frequency because we should not go above it, of course. And then another thing we care about is the signal-to-noise ratio, so we're going to check that, and we're going to keep to our criterion between 2 and 3, preferably 3 where we can get it. So we only work within that frequency band. And then we need to go away from the corner frequency. So we said that we define away as 50% above it. In this case, we would be working with a big earthquake, and this would be the acceleration spectrum. But if you consider the mini approach, where we work beneath the corner, then we just cut that down by 50% in order to be safely enough away from it, and in order to be able to assume that we don't have any trade-off, much trade-off between the source and what is supposed to be the site component in kappa. And finally, taking into account all of this, we need to be left with a delta F, so a range of frequencies wide enough for any sort of regression here to make sense. So that is fixed to around 8 to 10 hertz. So that's the end of the objective criteria. Then the second step is to compute the individual values of what I kind of called total kappa, so path plus site kappa. One of the considerations that was raised was how do we deal with the two horizontal components? And this is an example from New Zealand from a different study outside the NGA-East project, of course, where we happened to see that for 7 different sites in Christchurch, the measured kappa sometimes fluctuated with the azimuth. So here are our components which we rotated by 5 degrees and then recomputed kappas. So we found out that for some sites it's possible for kappa to depend, the kappa measurement to fluctuate very strongly with the orientation of the component. So what we want to do in order for kappa not to depend on the as installed orientation of the sensors is we use the vector sum Fourier spectra, and that way we get as close as possible to getting an orientation independent measurement of kappa. Then the next consideration, which was raised by John Anderson, is the use of moving windows, and that is to take care of the sensitivity of the kappa to which, really to the fluctuations of the spectrum as you see them here. So in other words, we want to try, wherever there's available bandwidth, of course, to use a moving window and get different estimates of kappa all along the window and compare it to the total kappa, which would be the kappa for the entire window, and then check that sensitivity, and based on that we can use the statistics to weigh the individual kappa measurements at the end, where we combine everything together in order to give bigger weights to kappa values that seem more stable with respect to these different windows. And then another consideration that I'm going to spend a little more time on is amplification. So these are just a couple of sketches to show what crustal amplification might look like for different profiles of generic rock. So you have your different rock profiles here going down to a few kilometers. And then these are different kinds of shapes of the transfer function that you may compute. So the issue is how do these affect kappa? So this is for the crustal amp, and then if we focus on the first few meters or hundreds of meters, then we have this sort of a fluctuation rather than this sort of a smooth increase in the VS. And this sort of a fluctuation in the VS can, of course, give you this sort of a shallow resonance pattern. So ideally, we would like our spectra not to be affected by any of this. And the big question is whether there is amplification or not. Is it significant in the frequency range we're going to use? So this is marked here in red, so we only care about what's going on between F1 and F2 where we're actually computing kappa. This, of course, only holds for the two methods above and beyond the corner. Obviously, for the broadband method that Walt is using, he will be interested in the amplification in the whole range, and he will be correcting for the function for the whole range, of course. So the question is, if we don't have, well, if it's near horizontal, it doesn't really bother us. If there is a non-horizontal shape, then it's bound to bias kappa. So if we have this sort of a shape, which is the most usual thing to have, then that means that the kappas we measure, if we don't correct our Fourier spectrum, are going to underestimate the true kappa. So after we correct for this, the kappa we measure is larger. And the way it's going to be done is the transfer functions will be computed by Walt with his Rascal code. This includes randomizing the profile according to the PEA approach. They'll be using the crustal profiles, given by the geotechnical working group. The important thing is to keep these amplification functions. We need to use them whether we're using the broadband approach or the acceleration and displacement spectrum approach. So this needs to be consistent for all the approaches. And what we're going to do is we're going to correct the individual Fourier spectra with the transfer function. So we're going to deconvolve it, and then we can perform the measurements as explained previously. And finally, after we compute all the individual total kappa values, the third step of the procedure is to interpret the individual values and get the kappa 0 and also the side component, and the Q, meaning the regional component. This is just a visual aid. It's not data from the NGA-East. So it's just to show, it's just an idea of what we want to do. So before we're able to do any interpretation, we need to separate data coming from different regions. Since the Qs are expected to vary with the regions. And then we will need to group similar sites with respect to VS. And then if we keep the stats from the previous, the slide where I showed you the moving windows, then we have weights for each individual point, and the more robust the individual values, the bigger their weight is, and all of these things are going to be taken into account when we try to regress the individual kappa values with Q in order to arrive here, which is kappa 0. This line is only indicative, obviously depending to the fitting with the data. It may be a different kind of we may have a different kind of a distance dependence, but we will only be able to discuss that in the final workshop after we have the results, of course. So I've also been asked to talk a bit about the difficulties with using data from the transportable array, and to do that by mentioning a few of the issues we faced when we worked on some southern Arizona data where we only had TA records. So here are some of the problems we had. I've highlighted the two main ones, and I'm going to go over those. So this is just an idea of the data we had from Arizona. If we go back to the first steps I mentioned with respect to the objective criteria for the definition of the usable frequency band, then the first thing that really cries out to us is the need to work within between the lowest and highest usable frequency. And when it comes to the TA, then that is heavily affected by the sampling rate. So here's an example of the amplitude and phase gain for the TA instruments. So you can see that the amplitude is only flat out to say 16, well, maybe 17 hertz tops, because the Nyquist is 20 hertz due to the low sampling rate of 40. So if we consider that, and then we consider the other need I mentioned to either lay above or below the corner frequency, this example I'm showing is for the acceleration spectrum method. So it's for the approach where we keep above the corner frequency and actually above 1.5 times the corner frequency just to be on the safe side. Then I've made this little graph to try and show you the effect of the uncertainty we might have in the corner frequency, which is due to the uncertainty we have in the stress drop. So this is just for a magnitude 3.1 we had in Arizona. And these two dots are the computed corner frequencies if we accept the point source stochastic model equations, and assuming two stress drops of 1 bar and 50 bars, which were the upper and lower credible stress drop limits we took for that study. So these are the two corner frequencies you have for that sort of a magnitude, and this is the lowest usable, the highest usable frequency due to the Nyquist. So what we can use, if we take this red scenario of a low stress drop, then we can use all this part of the spectrum from 1.5 of the corner out to 16 hertz, so the red part. If we accept the high stress drop, which gives us this high corner, 1.5 is maybe here, so we actually can't really use, well, really any of it. So this is just an example of how the stress drops and uncertainty can play into this. And the last major consideration is crustal amplification. So this is just a sketch of the different crustal profiles. And this was all work by Walt and Bob. And this is just a sketch of the transfer functions. And all of us used those transfer functions to correct our Fourier spectra. So we use them for the broadband approach and for the acceleration and the displacement spectrum approach. So keeping consistent crustal amp corrections, these are the results we got. So it's a rather complex figure, but the only thing I want to show here is these orange symbols here. So the kappa 0 that the broadband approach yielded was 33 to 34 seconds, for example. And after using the acceleration and the displacement spectrum, so methods, the other two methods, we got a model which is the the black dashed line, and the kappa 0 is almost the same as the broadband method, so 33 seconds. So this is all just to say that using the two different methods and keeping consistent crustal amplification corrections, we were able to use bad TA data to get, well, as consistent as possible a kappa 0 estimate. And I'll just close. I think I'm kind of reaching my 20 minutes here. So I'll just close with just conceptually how we want to use this Arizona experience to select the data we can use in the NGA-East. So you know the amount of data there is, but before going into each and every record, a clever thing to do would be to use this previous knowledge and see which records are actually usable with respect to the highest usable frequency of the records due to the instruments and the filtering, and with respect to the possible corner frequencies, which depend on the stress drop and the magnitudes of each event. So what we want to do is to use different stress drop scenarios. We assume a reasonable mean of around 160 for the central eastern U.S. To be a reasonable value, and then our upper and lower credible limits would be around 50 and 500. So we apply the lowest stress drop, which will give us the lowest corner frequency. In order to apply it for the acceleration spectrum, which means that we pull the corner frequency. Well, we make this red usable range as big as possible by using the smallest corner frequency possible, and then we assume the largest credible stress drop in order to run the kappas with a displacement method. So here's the displacement spectrum, here's your corner, and we try to have as high a corner as possible, so use as many records as possible. That obviously means that some of these estimates will be wrong for this case and some will be wrong for this case, but we don't have any better constraint on the stress drop. And the idea is to be able to create an overlapping subset between these two methods. So for the subset, both methods will be used, and we'll get lowest and highest credible kappa values, and that should help us get a handle on the epistemic uncertainty of kappa. So this is just an idea of the data set we have in the East. So these are your magnitudes, and these are your lowest usable frequencies in red, and your highest usable frequencies in black. So you can see that the highest usable frequencies vary enormously. You would have your TA data around here, and then better sensors would give you that. So the two lines I've drawn are the assumed corner frequencies for these two assumed stress drops. So with respect to these values from the flat file and these values for the corner frequencies, we will elaborate a procedure to choose the usable data from the NGA-East data set and then apply the two methodologies. Obviously, for the broadband method that Walt and Bob are going to use, they can use, well, they will start from the entire data set and apply their own criteria, but it will not be constrained by the problem in the corner frequencies. And I believe that's all.
Norm, and hang on, Olga, while I try to just talk briefly about how what you just mentioned is going to fit into how we're doing the ground motion models, okay? And then we'll take questions for Olga because she's on Europe time and we want to let her hang up and go to bed. The kappa model, once we have it, it's simple to put in the Fourier spectra. We simply put in a scale factor on the Fourier amplitude. Our goal is to have the GMPEs be developed for a suite of kappa values, so that kappa is a parameter in the ground motion model. So we need to do this work to get the pieces of the kappa estimate, but we'll be making the GMPEs have kappa as one of the site terms available in it. And so as kappa changes, or our estimates are different across different parts of the East, then you can start to account for that in the ground motion models. So that's going to be the way that this all fits together. Once we're doing Fourier spectra, it becomes a fairly straightforward exercise to bring kappa scaling into the ground motion models. Okay, any questions for Olga? John?
This is John Stewart. So I missed the introduction talk, so maybe this was mentioned before, but if I understood correctly, Olga is correcting the ground motions by a transfer function, a site transfer function, and then computing kappa on the corrected motions. Is that correct?
Go ahead, Olga.
Hello, John. So both, not only me, but also Walt and Bob are going to be doing that. So everybody's Fourier spectra will be corrected by Walt's amplification functions. Cross the amplification functions. That is correct.
So that means the kappas that you're computing are for the reference rock condition, right?
Well, the amplification functions are account for the VS. They do not account for the damping. They are done for zero damping. You still see the soil damping in there. The idea is to correct for the distortion in the spectral shape, if you will, which is due to the VS profile, so mainly due to the impedance or whatever you want to call it. But it will not all correspond to, 3,000 meters per second. The damping will be taken out afterwards. So the value that we get does not account for the linear crustal amplification, but it does include scattering and damping effect.
So hold on a second, Olga. So
yes.
John, one of the problems we have of estimating kappa from especially a slope of a Fourier spectrum is an amplification can put in a resonance that you think is due to the kappa slope, and it's not. So it gets tricky to try to get it. So what she's talking about is when she and Walt used the same amplification factors, then they had the same distortion, let's put it that way, at least consistently on the high frequency part, and they can then get similar answers. If you leave those amplifications out, then you're going to be treating bumps or troughs in the spectra as effects on kappa, and then you get into trouble. The damping is a whole nother issue in terms of trying to get the soil damping out, but usually that's not as big of an issue for most of these sites. Gail.
Gail Atkinson speaking. I was a bit confused by Olga's answer, and now I'm not certain. I understand that amplifications are removed, but I wasn't sure I heard the answer to the question, what's the reference condition to which it's removed? What's the VS30 of the reference site after removing the amplifications that were removed? Is it 3,000?
I am not sure what the crustal profile for which the transfer function is. I have not seen what the profiles look like for the east, and I do not know how deep they will go, to what VS they will go. But I don't know that I can say that the kappas we get are not conditioned to a particular VS30.
Bob, hang on. Bob Dara is here, Olga, and so Bob should be able to answer what was at least done for Arizona.
Yeah, so for Arizona, I have the pictures right here. The green.
Yeah, Olga, go ahead, Bob.
I'm optically challenged in the red-green part of the spectrum. Bob there again. So for the Arizona data, you can see on the left is the profiles down about 400 feet. And then we extend them to lower crustal upper mantle depths. So the velocity profiles go down to 4,000 meters per second in the west at great depth. And to compute the amplifications, we use the Rascal RVT program. We take the half space and the amplification to the surface and then just do division and smoothing. Similar in the east, we're going to use whatever the velocity profiles are for the east, and they'll be corrected down to 3,000 meters per second or higher. And then we just take the spectral ratio in the Fourier amplitude spectra. So it removes the amplification going through the velocity profile. So the Fourier amplitude spectra to surface has many parts. One is the amplification through the near surface velocity structure. One is also the effect of kappa on the profile. Well, all we are removing is the part through the amplification. So at very hard rock sites, if you had a site in the east that was at 3,000 meters per second, the amplification would be basically 1. We typically do sensitivity studies using, and we did it for the Arizona study, using amplifications of 1 and various amplification factors. We find that in the broadband study, and I think Olga's putting that up, our estimates of kappa are not very sensitive to the amplification. Part of the reason for that in Arizona was the limited bandwidth. We only went up to 16 hertz. In the eastern part, we may be going at 20, 25 hertz. But we have not done that analysis yet. Gotcha. So those are two of the amplification factors we used on the left-hand side of the screen.
So to answer Gail's question, I think it's relative to a profile. So not in Arizona, though. So in the Arizona profile, it would be a reference rock profile for that area. So in the east, we can use the 3,000 as a reference, but for Arizona, it would have been whatever that reference profile was, because everything is divided by the ratios from the site-specific profile to the reference profile, and that's deemed amplification.
Yeah. I don't know if the sketch does anything to help. Yeah.
This is Gail again. Then, so to follow up on that question, then I think it would be useful to look at that kappa variation by region, because I find, well, I look at those results and I find, 0.02, 0.03, that is about what I would expect for a kind of a soft rock condition, and that's what I would expect you might get for a lot of those. But I think if you were looking at kappa naught values for hard rock sites in the east, 0.02 is high relative to expectations and from other studies. So it would be interesting to see why that result is being obtained and what the interplay or the correlation might be between those kappa naught values and the crustal profiles and the regions from which they're coming.
I think that the transfer functions will definitely be computed, taking into account the regionalization, given that the underlying rock would not really be the same, say, near, I don't know, for example, Mississippi or Canada, right?
Bob, there again, yes. Christine's given us the regionalized Fourier amplitude spectrum for the east. So we will be computing kappa in the regions we can. It doesn't look like we'll be able to do anything with the Atlantic coastal plain, for example, but the other regions will be computing kappa region-specific.
Yeah, this is Gabriel Torre. I'm not speaking as PPRP member right now, but just to add to the clarification, and if you think of how you use this kappa in a forward sense, if you don't remove the amplification, then you will be including those crustal effects twice, because first you put it, you start with a room spectrum, you put in the crustal effects, you put in the kappa, you get the motion. So it's important to do it this way, to remove those crustal effects from the kappa analysis, because otherwise you'll have them in twice.
Thank you. Is there any specific question for Olga before she's difficult to reach? Okay, so Olga, thank you so much for joining us and staying up, and we appreciate it. So here we'll have a break.
Thank you.
Okay, thank you. We'll have a break, 15 minutes. What time is it now? 10:20. Okay, so let's do a 10-minute break, and then we'll come back with 2 short presentations and questions and discussions. If you have not signed up, please sign up front. Okay, so the next 2 presentations, following what Norm has shown, in NGA-East we're developing new GMPs, and now we're talking about 2 duration models. The first one is by Nico Kuhn, who's going to talk about how to Kuhn, again, Kuhn, Nico Kuhn. Okay, good. Thank you. It's going to talk about how for more the empirical model that we're developing, empirical with seismological constraints, and how we're going to define the duration that is consistent with PSA. The second talk is from Dave Bohr, and that's on the SMSIM approach. He's revised his duration model with the NGA-East data, so he's going to talk about that. So those are really two new duration models. For the Silva model, they're going to use duration models that they have already. Okay, Nico.
Thanks, Christine. And so what I'm going to talk about is going to be very quick. It's basically something about a paper that mainly Sanjay did for European data. And I'm going to show you mainly examples from the European data because for the NGA-East data it hasn't been done yet. And so this should really be, it's about what Sanjay has been done, and apparently I'm getting old enough to take credit of other people's work. Whatever, but just that's the idea. Okay. So what Norm already said, the main motivation for this work was that the Fourier spectrum is easier to understand than the response spectrum. So we decided to build an empirical model for the Fourier spectrum and then combine that with a duration model to get the response spectrum. But we also said we don't really care about the duration. What we really care about is the response spectrum. So therefore we tried to find a duration that is optimized to give the smallest misfit between the empirical response spectrum and the response spectrum that was developed using the empirical Fourier spectrum model. And then we combined the duration model together with empirical Fourier spectral model with RVT to get the response spectrum. And the basic idea is in this paper, which was published this year in the Bulletin of Earthquake Engineering. Just to recap about random vibration theory, what we want to do, we want to calculate the maximum response of a single degree of freedom system, which is here written by Ymax. And to do that, we need a couple of ingredients. The first one is we need to calculate the root mean squared response of that system, YRMS, which is just the square root of the zeroth moment of the Fourier amplitude spectrum divided by the DRMS, which is the root mean squared duration. And we can just calculate the zeroth spectral moment and all the other spectral moments that we need by this formula here, which is just an integral over the Fourier spectrum. And then we need a peak vector that relates YRMS to what we want to know, Ymax, and then we can just multiply YRMS times P, which gives us Ymax for each frequency. And there are different relations for the peak vector, and the RVT group has decided to use this one, to use the original one by Cartwright and Longway-Higgins, which is, no? Okay. Which is this one, but there are approximations to this one. This should actually be an integral from 0 to infinity. And there are two main ingredients in this, which is NZ and NE, which is the number of zero crossings of the response and the number of extrema of the response. And these can be calculated by these two equations. And there we have a duration in there, and we have the ratio of the spectral moments of the Fourier spectrum. And what's important is that this duration is a different duration than the duration that we had before, the YRMS duration. These are just the basic ingredients that we need for RVT to calculate the response spectrum. Okay, so we need two durations, DRMS and the ground motion durations. And basically, what has been found is that DRMS is a function of the ground motion duration. And there exist several models for that by Joy Nambour, Pezesh, and Thompson. And I think there's a new one developed using NGA-East data for that one. And once we have a model for that, and once we have a model for the ground motion duration, we could easily calculate DRMS. possible choices for the ground motion durations would be something like the 5 to 95 or the 5 to 75 duration. But what we did is we said we don't care if the duration is actually a physical duration. All we care about is that it minimizes the misfit between the response spectrum and between the response spectrum obtained by RBT and the empirical response spectrum obtained directly from the acceleration trace. What we do is we're going to invert for that duration that does that. We're going to try and find the best duration that minimizes this misfit. That's not a physical duration, but it has some, in the end, we can compare it to D5 to 95 or D5 to 75 and see how it relates to those. And then the examples I'm going to show is from work done or from Bora et al., which is actually from 2014, which was applied to the European database. Okay. So what we have is, so this is just an example of that, trying to see if we can actually do that. So this is a response spectrum and a Fourier spectrum generated using SMSIM. And we have our target, which is this response spectrum. We have our input, which is the Fourier amplitude spectrum. And then the parameter that we're inverting for is the ground motion duration. In this case, the SMSIM duration was 1.638 seconds. And how do we do that? What we get out is this value. So we get out the 1.675 seconds. And what we see here is overlaying the original response spectrum and the response spectrum obtained using this 1.675 and using the Fourier spectrum. So it works pretty well for synthetic data. This is an example using real data. That's from the NGA-West dataset, which has the ID number 12. I don't really know which record it is. But what we have in black is the observed or the empirical response spectrum. And in red is the response spectrum obtained from the Fourier spectrum and the duration that we inverted for. And there are some errors that we have, but in general it works pretty well. Okay. What we then get is we get something like this, where we have durations for all the records, and then we can plot them against magnitude, against distance, and then we can fit a model to that. That's what we did in the original paper, is where we used this particular functional form to model the ground motion duration. And this was based on other duration models. So the functional form was based on other duration models that were published in the literature. It works pretty well, but the question is, should we use something else? So should we use a duration that's more physical, based on source duration plus path duration? The thing is, this gives a much better fit to the data, a functional form like this, but it might not be extrapolatable. And that's the thing we need to kind of figure out in the end what we're going to do. In the end, what we also need to think about is our target is still the response spectrum, so we need to find the functional form that best predicts response spectral data and not necessarily that best predicts the duration. That's just some of the things we need to figure out. This is just how it compares to other duration models. So in black, which is this line and this line, is the duration obtained from the inversion. And here we have in blue and in red, we have the duration from Bommer et al., which provided empirical models for the 5 to 95 and the 5 to 75 duration. And our duration is kind of in the middle of those. I don't really want to interpret that, but that's just the way it is. So what we then have, we have the Fourier model, which gives us the median prediction of the Fourier amplitude spectrum. And then that needs to be adjusted for the mean. Noam talked about that. And then we combine that with the duration model, and then we get a response spectrum. And this is shown here. So this is a response spectrum. Again, in black, we have the results from the paper using the combined Fourier spectrum, empirical Fourier spectrum model, and duration model, and the other lines are other empirical models for European data sets. And we are kind of in the same ballpark. But there are, of course, other things like the other studies use a different data set. They have a slightly different functional form. But the general thing is we're kind of okay in terms of a response spectral model. All right. So then these are residuals of the response spectral data to the response spectrum obtained using the Fourier spectral and RVN duration model. And again, we're kind of okay. When we calculate standard deviation on that, they're pretty high in this case. But Sanjay has been developing the model and using additional predictor variables, also incorporating kappa in the Fourier spectral model, and that really brings the standard deviation down of the response spectrum. But that's just to show you the approach works. We can build a nice response spectral model using a Fourier amplitude spectrum and an optimized duration model. If we actually we've done that. If we use a different duration, if you use it like the 5 to 95 duration, we get much larger residuals for the response spectral data in this case. Okay. So again, Norm talked about this, so I'm just not going to show this, but we need to be careful that we're using the mean in the RVT framework, whereas when we're using log normal distribution to model the empirical Fourier spectrum, it will give us the median. We need to adjust that, which is this times e to the power of sigma squared divided by 2. And the sigma that we're using is a combined sigma out of the smoothing and out of the regression. Because if we smooth, then we'll just reduce the variation in the Fourier spectrum, and that will then reduce this part here, so this regression sigma. All right. Issues that we need to talk about, or that we need to think about, is the usable frequency range for the estimation of the duration. The usable frequency for the range for the Fourier spectrum is pretty low. The question is, should we try to build a model for the FAS, extend the FAS outside its empirical usable frequency range, use that one to calculate the duration, and then also calculate the empirical Fourier spectral model, yes or no? We need some sort of model for the relation between the RMS duration and the ground motion duration. So what we did in the paper is we used the Boer and Thompson coefficients, but in the end it doesn't really matter, because if we use a different model for that, we'll change our inverted duration. But if we then use the same model to calculate the response spectrum, it will be internally consistent, and the response spectral field will still be the same. So that's actually, if you do that, if you use a different model, you always get a slightly different duration, but your fit to the response spectrum will actually be the same. So it just means we just need to be consistent. The other thing that we can think about, and which actually reduces also the fit quite a lot, is we can use a frequency-dependent duration. So that means instead of having one duration that minimizes the overall fit of the response spectrum, we cannot optimize the fit for each frequency individually and get a frequency-dependent duration. That means we would need to develop a frequency-dependent duration model, just like the empirical GMPE model. We can do that. I'm a bit worried about overfitting in this case, but it's something that we might think about, because it reduces the variability of the response spectrum a lot. The peak factor, we just need to be consistent between estimating duration and then later estimating RVT. Whatever peak factor we choose, we need to stick with it. And there are some advantages of using a simpler peak factor or an approximation, because that's actually makes it easier. You don't have to perform this integration of the original peak factor, which might make it easier for some kinds of inversion and other things. But in general, what we need to be is we need to be consistent with the Fourier spectral empirical model. So we can't estimate the duration based on the Fourier spectrum, which is not used in the development of the empirical Fourier spectrum. So whatever is decided there needs to go into the inversion of the duration. Okay. But anything, so any slight, I don't know, any issue that we have or anything that we might do wrong will get absorbed into the duration. In the end, we still, whenever we get a good fit of the response spectrum obtained from the duration and the empirical response spectrum, we are okay. And then we just need to check that this is always the case. Okay. So this is just one of the issues, or one of the things that Sanjay has been working on, is extending the usable frequency range. What he did is he fitted a physical model to the Fourier spectrum, and then inside the usable frequency range, he used the empirical Fourier spectrum, and outside he used the fit. And then that way he can extend the usable frequency range, which was in the original up to about 50 hertz to about 100 hertz or 200 hertz. Again, we might actually overfit, so we just need to worry about that. But this is something we need to keep in mind, and we can try to do that. The other thing is he used a different functional form now, which is based on, so this is based on the work that Dave Boer has done, using a more physical form for the duration model. It actually gives not as good fit to the duration model, but the idea is that this allows to better extrapolate the data. And he also used a frequency-dependent duration now. And in the end, this reduces the variability of the final response spectrum model quite a lot, and even to the point where I think I don't trust these numbers. But, right. So that's just basically the idea. We haven't done this for the NGA-East data yet, but we can make it work. So we can just estimate, we're just estimating a duration that optimizes the response spectrum fit. There are some things we need to keep track of, but in the end, we will end up with a response spectral model that should capture the response spectral data. Thanks.
Thank you, Nico. So there's a lot of course, technical issues just talking about those peak factors and the choices we make and all that. And we decided to leave that out of this more big formal meeting. This is getting resolved internally with the RVT group, and we'll keep you informed. But yes, we're using the Denmark peak factors.
Okay.
So, okay, this is something that we can share at a later time when we have a conclusion on our working meeting process. Are there quick questions? Does everybody see what we're trying to do here? What Nico's proposing is basically, if we have the recorded time series as we do in compute PSA, or if you take their FAS instead and find the duration that allows you to match the same PSA, that's the duration model. So that's where we have data and bandwidth. Are there questions for Nico? That was very clear.
Good.
Thank you very much. Okay. So we're going to now have Dave Boer come over and talk about the duration model as it is calibrated to be used within SMSIM.
Well, good morning. I'm going to talk about a somewhat simpler model than Nico just talked about. And I'm going to give you a little background here, just a few cartoon-like slides talking about the simulation method, the stochastic method. Probably most of you are aware of it, and you've probably seen this slide before a number of times, but the whole idea is that you combine a deterministic target amplitude with assuming that, that the motion is spread over some duration, and the key thing here is the duration that we use. And let me see. So this is actually showing real results, but it's kind of a cartoon anyway. It's the basis of the stochastic method. In this case, I'm showing a target amplitude spectrum for two magnitudes, a 4 and a 7, and you assume that that motion is distributed over some duration, which is a summation of the path duration and the source duration. And then you get the seismograms that you can see down at the bottom. If you look in some more detail about the steps we use, we generate random noise over a certain duration, and then we window that noise. That's the upper right-hand curve. Let's see, I guess I have a mouse here that I can show you. Yeah. And then you go into the Fourier spectra, you normalize the root mean square of that windowed noise to unity, and then you multiply it by your target spectrum. And then you go back in the time domain and you have your Fourier spectra. So the important thing here is the duration you use, and that's the subject of this talk. I have, and by program, two ways of doing this. One is just a box, so it's just a, just random noise, and you cut it off on either end. To make it look more like a seismogram, I also have one where I call it exponential window, which is using some results of Saragoni and Hart from many years ago. And there are a number of parameters that describe the shape of that window, and this is showing what those parameters are. I don't expect you to look at those in detail, but I've generally just fixed those parameters, and but I also, an important thing here that I had actually forgotten about was in my original 1983 work, the parameters are such that if you do a simulation and you take the Hused plots and you take the 95 minus 5% duration from the Hused plots from your simulated time series, that on average that will give you the same as your input ground motion excitation duration. So all of my SM-SIM results are based on a 95 minus 5% duration. And that's an important thing to keep in mind, because when we look at data, and this is real data, the second time series here is the seismogram. This is the Hused plot on the upper one. And if you take 95 minus 5, you notice that there's a pretty strong P wave. And so actually, the duration you're getting is a combination of the P wave duration and the S wave duration. And the simulation method only assumes S waves. So what we found in our analysis is that we couldn't use from the data, we didn't want to use 95 minus 5 durations. What we ended up using instead was 80 minus 20 to try to avoid some of these issues of the motion starting early and then extending for a longer time than you might expect because of maybe surface waves or aftershocks or something like that. We also found that we could convert that to an effective 95 minus 5% duration by simply multiplying by 2. So that's the upper equation I'm showing here, and I call that D95 prime. And then we want the path duration, so when we take these observations that we have from the database, we have to subtract off the source duration. And the source, if we knew the stress parameter for each earthquake, that would be great. Then we could subtract off the inverse of the corner frequency corresponding to that stress parameter, but we don't know that. So what we've done in our work in the West, which is in press right now, is we use the Atkinson and Silva model, 2000 model, and as the source duration. And in the East, the new analysis that I'm going to show today, we've simply used a source corner of 250 bars, a single corner frequency model, or 400 bars. It doesn't really matter because the durations are so small and the earthquakes we're using are so small that it doesn't really matter very much. So here's the results. What we've done is we've taken the database that Christine has provided where people have calculated the various durations, and we have computed this D95 prime, or what I call here D95 scaled. We've subtracted off a source duration, and what I'm showing is the median values in different magnitude bins. So, like the inverted red triangle is magnitude 3 to 4. The blue diamonds are 4 to 5, and so on. And then this is a function of distance, rupture distance. I'm also showing the results we got from the analysis of the Western data, which are given by the pluses and the crosses, and the solid circles. And you can see that they're very different. And this is one of the things that we're finding is that the eastern durations seem to be much larger in general than the western durations. Not at all distances, but certainly at this distance range. I'm also showing the model that we fit to this, and that's the heavy black curve. And that we would call our new proposed duration model for simulations using the stochastic method, at least as developed in or is used in my program. And then for comparison, the magenta curve shows the curve that Eric Thompson and I have derived for the western data, active crustal region data, and then the gray curve is the duration model that Gail and I have used for a number of years. So you can see it's quite different. This is out to 100 kilometers, the very same data. Oh, by the way, the cyan, little cyan points are individual individual observations of the durations for the magnitude 4 to 5 range, which we feel like we're guiding most of our results based on that. This is the same data, but going out to 300 kilometers. And now you can see that once you get out to around 250, 300 kilometers, the west and the east data actually come together. And this is going out to 1,000 kilometers, or 900 kilometers in this case. Just to show some of the consequences of that, I did simulations for magnitude 5, 0.1 second response spectra as a function of distance, and the red curve shows what we get if we're using the Atkinson 04 geometrical spreading in Q. We're using the Atkinson Bohr 95 duration model, 250 bar stress parameter. If I take all the parameters being the same except for the new duration model, you get the blue curve. You can see it's lower, which is no surprise because the duration is longer, so the energy is being spread out over a longer duration and you have lower motions. In order to bring those back up to the 250 bar, the previous duration model, you need a stress parameter of at least 400 bars. So there is an important implication here in terms of fitting data, and to the extent that the previous model fit the data with a 250 bar stress parameter, that means if we're using the new duration, we're going to have to adjust the stress parameter. This just shows some simulations at 0.2 seconds now for magnitude 4 and a magnitude 8 as a function of distance. And the difference, again, is I'm using 400 bars in this case. I'm using the new Atkinson and Bohr 2014 geometrical spreading in Q, but I'm using the two different durations, the older duration and the new proposed duration. You can see that the difference, or the impact of the duration is more important for the smaller earthquakes and closer distances, which is what we would expect. And the other things I've used in here, which is an oh, by the way, you should pay attention to this, and Norm talked about it a little bit. The effect of, I've included what I call a finite fault factor. Norm called it a pseudo depth, and I'm using NEA and Atkinson 2014 results that are in press right now for that. And you can see that has a huge impact on the magnitude 8. It means that there's very little distance dependence to the magnitude 8 because the finite fault factor is on the order of 50 kilometers. On the other hand, for magnitude 4, it is trivial because it's actually less than a kilometer. However, I've also built in here a depth. I'm not going to call it a pseudo depth. I'm going to call it an effective hypocentral depth, which is magnitude dependent because the plot here is the abscissa is RJB distance, horizontal distance, and my idea was that it's unlikely you could, for a small earthquake, that you get an RJB of the earthquake, if you're in at, say, 0 kilometers RJB, that a small magnitude earthquake is not going to be up near the surface. So you would want to put in an effective hypocentral depth that captured that effect. Whereas for the large earthquake, it would probably very likely come near the surface. And so there's a hypocentral depth as a function of magnitude that's built into this. So these are considerations that doing forward simulations for this project, people have to think about. And that was for 0.2 seconds. This is for 2 seconds, and we see very much the same thing. And that's all I have.
Okay, yes, Gail.
This is Gail here. Thanks, Dave. Just a quick sort of comment, which also leads into a bigger question. Just at the end there, you were making the comment on the effective depth question that a small magnitude earthquake would not likely be very close to the surface. A case where that may not be true is when we start considering induced seismicity. If we have an induced magnitude 4 or 5 earthquake at shallow depth, and this raises a question that I'm not sure we've actually talked about before in this project, is whether our ground motion prediction equations in fact want to cover the potential scenario of moderate induced events at very shallow depths and potentially very short hypocentral distances. Maybe Norm might even speak to that, or Christine, whether there's been discussion of that, since in fact it may be in some places the largest hazard, I might say.
I think the short answer is yes, that these models will be used beyond just the nuclear application, and so if you're handing them to the USGS, they need to be able to calculate those kinds of, that case. So we should not say that's not an applicable case for us. We'd like to make models that can reasonably be applied to that range. Yusuf is grinning over there because I don't think it's a huge effort. It just means we need to pay attention to it. Because I think a lot of what we saw in the fictitious depth before was just because we didn't pay attention to that case.
Yeah, I agree. It's not necessarily a huge effort, but it does have huge implications. And I think a plot, Norm, that you showed earlier, where you showed the difference in your model in the fictitious depth and how that scaled down to the moderate magnitudes, that's going to be absolutely huge if we start talking about earthquakes that might be close to the surface in the moderate magnitude range.
This is Rob Graves. Just to add to that discussion, I think the induced seismicity issue is important, and if we can address that, that would be worthwhile. I think we would also need to account for possible stress drop differences for these induced events in addition to this fictitious depth. So it becomes a very complicated problem.
Yes, if they exist, which we don't know.
So what we said we would do for this, so Rob's solution to this was we can delay the project, but we can't. So we're going to use the data now, and we're going to try to see when we look at the data and do the residuals and all that, we'll check it. But right now we keep the triggered or induced events in there. And as more work is done on the stress drop, it's not something we can address in just a few months, but there are plans for that for NGA-East 2.
Am I done?
Any specific question for Dave? CI team? Happy? Okay. So thank you very much, Dave. So we're at this time where we have an hour for discussion on everything we've seen this morning. And that goes back to the plan that and the proposal that Norm put up there. So now is the time. Walter.
So Dave Bohr. Hi, Dave. Hi. You know, No, she said that we should limit the number of questions while the speaker's up there. You know, the concept of a distance. Oh, we need that slide.
Yes, okay, it's there.
Walter Mooney, in case you're not in the room. So the concept of a distance for a magnitude 4 is very clear because a magnitude 4 is almost a point source. But then the concept of a distance for a magnitude 8, since it's I mean, you sort of mentioned it, and you gave it a rupture length of only 50. I would assume it would be usually longer than 50, like 150.
So this is a very important consideration for point source simulations, and it's something that a lot of people are looking at now and have looked at in the past. And you can do finite fault simulations. In effect, what you're computing is a root mean square distance from the source, from the site to the source. So you're accounting for the fact that most of the motion that's arriving at your site is coming from points that are not the closest point to the fault, but are farther. But it's also not the maximum extent of the fault either. So in some sense, it's a compromise. So the 50 that I came up with is actually based on analysis of real data. It's also similar to some results that are obtained with simulations, but it's primarily from data from a paper that Gail and her graduate student have in press at this point, and also consistent with work that Norm and Carla D'Alessandro and myself have a paper that has analyzed some of the motion that was used in the SKEC broadband platform validation exercise, and we find very similar numbers for this finite fault factor to what Gail and Emra NEA found.
As you know very well, the shape of that curve for the magnitude 4 is going to be highly dependent on the focal depth. So the curve, you know, the shoulder at 60 kilometers will move towards the shorter distances as the event gets down to a depth of 20 or 25 kilometers. And we do have those kind of earthquakes in the central and eastern U.S. So I think that kind of curve really almost should say m equals 4 parentheses z equals 5 or something like that. About 8. I was off by 3.
Because in Dave's simulations, as well as many others that we're going to be trying, the parameter that's really coming into play, as Dave pointed out here, he had to go from a stress parameter of 250 to 400 bars. And that effectively shortens the duration and the like. And this is really playing into what Norm talked about earlier, where the duration has to be looked at, or what Nico was showing. So this stress parameter, and is going to become, I think, a real key issue if it is depth dependent or not depth dependent. I think that this is going to become something, and on a big fault, I mean, maybe there isn't one single stress parameter. Maybe, you know, it's variable, so it's going to be very difficult to sort out. But that stress parameter it keeps increasing. I don't remember 400 before in the past. I mean, numbers for the east were a lot lower than that, and then they keep going up, and recent simulations were 1,600, in fact, in one case. So they're getting up there.
This is one case speaking. I think, yes, this is Gail speaking. Yeah, Ralph, that's an important point, and it also feeds into what Norm said, is that we have to keep the attenuation and the source parameters together, because pretty well always when you have those higher stress value, they're coupled with a steep near source attenuation, and Norm was showing, in fact, their results in their preliminary regressions of r to the minus 1.2 or something like that, and so that would be coupled then with this higher stress, and Dave's stress drop of 400 bars that he was mentioning then is also coupled with our more recent attenuation Fourier attenuation model that has r to the minus 1.3 near the source. So I think as long as you keep those two things coupled together, and again, think in the stress parameter, I think it should be thought of in a similar way to what was just mentioned earlier about the duration. It's not necessarily a strictly physical parameter. It's essentially a fitting parameter that carries the units of stress or the units of duration, but has actually a much fuzzier meaning.
And is, in a sense, tied to a specific model and all the assumptions that go into that model. So that's the other thing we need to keep track of, is that 400 bars is specific to that whole set of parameterizations, and we can't say, oh, somebody else had 500 bars. Those two may not be the same.
So in that respect, also for the duration model, one thing I like about this is you have the duration is still parameterized into a source and a path effect in that sense. Something we lose when we do the inversion a la Nico. But these two things are complementary, but this allows to make sure the magnitude scaling is probably better. And on the stress parameter, yes, the duration, because we're going to, even within SMSIM, we're going to span a range, we should have the durations that track with that as well as correlated sets.
Are you on, Gail, or am I on?
So in our correlated sets of coefficients, we've added a duration model, right? That's one thing that comes out, that all has to be internally consistent and done together. What Christine talked about, I am most concerned with our calibration of this and how it extrapolates. What is the basis for extrapolating that to higher magnitudes? And we can use what's in the simulations to see what they would give. I don't know if those all fit together, or if those are two really different sets that may not be the same thing. I think that's going to be one of our real struggles in trying to make this whole approach work.
Yeah, that's a good point. And one thing I was glossing over here, especially like this up there, I'm using the duration model that was for these small earthquakes, basically 4 to 5, for which the source duration is not important. I mean, you're basically able to isolate the path duration fairly directly. But when we do the simulations for the big earthquakes, sure, I'm using an effective finite fault factor or pseudo depth to try to account for the fact that most of the action on the fault is coming from greater than the closest distance to the fault. But the duration might also be different. And so, I haven't thought about that. And it could be that the duration should be magnitude dependent. And this is going to be, in order the way to assess that is to do simulations, finite fault simulations, and just look at that.
So this is Nico. This is something else I wanted to talk about. And Norm said we need to have constraints for the model in order to get all the correlations right. But a fixed constraint is nothing but a very, very strong prior. So, and you also showed the simulations from the uncertainty of the coefficients, which is conceptually similar to samples from a posterior distribution. So why not go directly to a full Bayesian approach of estimating models, which would give a clear probabilistic interpretation of everything, and also makes it easier to keep, or in my view, makes it easier to keep track of all these uncertainties, especially when we're combining uncertainties of the Fourier spectral model and the duration model. And the question is also when the uncertainties in the median predictions were pretty large. So what are we going to do about it? Are we just going to take the mean median predictions, or are we keeping track of the full uncertainty. And in my view, it's easier to keep track of that in a full Bayesian approach. And then you don't have a fixed constraint. You can have a strong probabilistic constraint, but the data can still draw it away from the prior.
I think every time we do GMPs, when we build models, we've said this isn't purely statistics. There's a whole model building exercise. It's implicitly Bayesian, okay? And I fully agree. When we put in a constraint and say, I'm not going to let that parameter go negative or positive or whatever it is, I am imposing a very, very strong prior. And you can relax those to some cases, and we generally stick with it until the data push us off. So we're doing Bayesian methods by hand, right, in a crude way. To answer your question, do we need the uncertainties? Yes. That's the focus of this whole approach, and what we're trying to do is to lay out the uncertainties and what is the range that is consistent with the observations and consistent with our strong priors, again, or whatever the range of the seismological constraints that we truly believe. As we go outside these data ranges, we're going to have exploding uncertainty. That's unavoidable. But that's what we need to do. So I think we're probably working in that framework and not doing it as formally, and it may be just as easy to jump in and do it in a Bayesian framework as opposed to, let's say, the judgment-based approach to Bayesian that we do now. But I think we all are doing Bayesian analysis whether we say it or not.
But I think what Nico is proposing is to do it from the start, even in our FAS space, and do everything in there, and then constrain later. But another way to look at, if you go back the way I always thought about epistemic uncertainty, which we'll talk about tomorrow a lot, okay? You have those different correlated sets of parameters, and you run, and these lead to different models that then you try to put weight on. But that's a very kind of discretized approach of looking at things. But you wanted to start letting it go? You don't want to enforce a prior? Okay.
I'll speak for Nico, then you can correct me, okay? But the whole point is we impose priors all the time, and they tend to be absolute. So we have either a 0 or a 1 weight on our priors. Okay, what he's suggesting is set it up more formally, make it 80% weight on the priors. It's very strong, but then when the data is really pushing you off, it starts to push you off. It's no different than how we've been doing it, other than formal as opposed to more ad hoc in terms of how we've done this type of an analysis.
Right. So an example would be the normal faulting factor in your NGA-West model. Instead of saying it is 0.1, you could say, okay, it's 0.1 plus minus some normal distribution, and you can make this uncertain, this standard deviation of the normal distribution very, very narrow, and then it's a very strong prior. And but it's still that if the data is different, it would shift it a bit to lower values.
While we have Nico here this year, we should take advantage of that and start to implement something a little more structured. I think that also fits with what we'll talk about in terms of the uncertainty treatment tomorrow.
So, John Adams, do you have a question as a participant? Resource? Okay, good.
John Adams, Geological Survey of Canada. From my experience of earthquakes in basically northern Ontario, nearly all of them are in the top 5 kilometers or so. And I think that it's not just induced earthquakes we need to worry about. We could easily have magnitude 5s in the top 1 or 2 kilometers. And so if they're not going to be modeled correctly by this, will you explicitly say so? And then the second question is, in the simulations, do the surface waves, the RG from those earthquakes, get calculated or not? Because they have quite a significant kick in the mid-band, say 0.5 seconds, or shorter periods, depending on how shallow the event is.
Thank you. Well, part of an answer, I guess, is that recorded events, we have the information, the metadata that goes with it, so we keep track of that. We can look at it. But yes, so shallow events are in there. Now on the simulations, I guess we'll be able to talk more about that tomorrow afternoon when we're going to look at the different methods that are used. Some allow formal propagation and others, I guess, not formal. Yes, Ken?
Ken Campbell. So just to be clear, I'm a little confused at this point. I mean, I understand all the presentations, but as far as the final GMPEs, are they going to be in terms of Fourier spectra? And then if you want response spectra, then you have to apply these other, the duration and peak factor values, or those are going to be applied in developing then the response spectra GMPEs?
We have a very special event happening right now. Norm's phone is ringing. It never happens. He's answering. This is extreme. Okay. Okay. Yeah, he answered a couple times the last few weeks. I was like, wow, you're here. Okay. So, so just to clarify, we developed the models in FAS space, but then what we give as a final model is in PSA space. The FAS just allows us to propagate everything, especially the kappa, that otherwise is mapped too widely to be really distributed on the right PSA frequencies. The final models that people will see will be in terms of PSA, but they will have been constrained in FAS. You need to be Canadian to operate those microphones, obviously.
Just one question, and I cannot enforce it being PPRP. I encourage you to polish both, the FAS model and the SA model, because each one will be useful in its own way for its own purposes.
Absolutely. This is true, and since we've started to explore this, we always have in any event the PSA in our back pocket. If for some reason something becomes insurmountable in the time we have the PSA models as well. Yes. We're going to do both in parallel.
And you may say that in case there are differences, one of them governs. But having both will be very useful.
So, Jake, just to make sure, you meant publish the steps of GMP for Fourier spectra and obviously final results for PSA, or you meant traditional way of GMP for PSA?
I say, I mean, when you get to publish the results in the report, it would be nice if both sets are there. So if somebody wants to work with the PSA because they have a rock site, then they can use those. But if somebody needs to do IRVT to adjust for kappa or whatever, they can use the other one.
So, yeah, the steps are obviously will be documented very well.
Again, yeah, don't treat the Fourier amplitude as an intermediate result that you don't document to the same extent. Document both to the same extent, but also say that in case of difference, one of them controls.
Absolutely.
Which one controls?
I was answering to a different question that if we can't make it happen, we have to be realistic, right? We have just a few months to do everything. It looks good so far. We think we're ironing out everything. I think it looks good. But I answer your previous question. We're also going to look at just PSA. But yes, definitely in the documentation, we're not just going to publish, hey, here's the equation. I think both steps are going to be there.
The documentation for the Fourier spectrum will be much more extensive. That's where the judgments and the extrapolations and evaluations are all dumped in there. The PSA model really should be something I could hand off to anyone and just a statistician say, just fit this data because it's all interpolation, right? At that point, they can, as I said, you could simply parameterize those in the way we normally do it, or you could do non-parametric forms because it's all interpolation. So I see the response spectra report being a much simpler one, just saying, we had these values, here's an adequate fit to these. Right? A table, a lookup table is what Bob just said. And we have to bring along the other information brought on the response spectrum report is the standard deviations. And so that needs to be in response spectra space, and that has to have its own evaluation of the data and or transportability of global sigmas to the east.
So, Scale, just to expand further on that, following Gabe's point, then if we do, in fact, have the PSAs available as lookup tables, which I think would be very useful regardless of whether parametric form ends up getting fit to it, it would be very nice to have the corresponding lookup tables for the Fourier spectra.
Sounds easy, but so you're saying you will have two GMPs, one for Fourier, one for response. That's the bottom line? Is that what? Okay.
We tend to call GMPEs or think about them only in response spectra, but there will be a model of the Fourier spectrum that depends on magnitude and distance and other stuff. Okay, that gives you a median, and it has the standard deviations that we can compute the squared spectrum that goes into RVT. Right, but you could also do whatever, as Gabe said, if somebody wanted to do their own kappa adjustment, it's a lot easier for them to do it in the Fourier spectra. But we are planning to have that as a parameter in the Fourier spectrum. So if you said I want a kappa of 0.015 instead of 0.008 or whatever, you just put that into the Fourier spectra, and then it should pop out, all right, in terms of the parameterization.
I think just following up on Linda's point, to avoid confusion, I would recommend that we don't call the Fourier spectra models GMPEs for Fourier spectra, because that's going to cause, I think, a tremendous amount of confusion. So I think if we call the Fourier something like the table of the Fourier models, or it's an intermediate tables, and reserve the use of the term GMPE for the response spectra model, just to avoid confusion. Otherwise, we're going to end up with people grabbing the Fourier spectra model and thinking that they are doing response spectra. Wait for it, it will happen.
You convince me. We're going to call them regression models or something, or I don't know. We have to find another. FAPs?
Fourier amplitude prediction equation.
Prediction equation? Okay.
We can think of something better.
We'll think of something that sounds good. It's modeling. Yeah, FAM, FAM. Okay. We'll start the working group to find the name for that. Just kidding. We could have a contest, and whoever wins it gets to use the equations first. Okay. So, what time is it now? 11:30. Okay, you guys have to be more curious and inquisitive because we have half an hour of discussion. Questions, issues. Okay, Nico is going to change the world around again.
Yes, I mean, so Nico, so we've talked about that eternally, but what about random effects on the regions? I just want to say that it might be possible, and then we would borrow strength for regions which don't have a lot of data from regions which have a lot of data.
So yes, this is something we want to try. So when we do the random effects regression, we take the event term out, One other mixed effect is looking at our regions and data in what we call regions that we'll discuss this afternoon, and see if that comes out straight out of the regression if we have a regional term. This is something we want to look at as well.
Go over to
Rob.
Rob, but let me just say, for the regression analysis that we're doing, the recurring issue we have is that there are multiple random effects which are correlated. And we've been using random effects one at a time, and depending on which one you do first, you may be messing up the other. So it will be a big step forward if we can put in multiple random effects and get the models to converge. Otherwise, the big features are the random effect on the source term. The site term we know is very strong. And then the regional term, which is basically the R. And I don't know if it may be more than region. It could be a random effect on the slope by event, because we sometimes are getting different slopes coming out. Also based on depth, for example, it can be changing what the slopes are. So when we try to do it with regions, our current regionalization has so few data in a couple of the regions that it's not very informative, but the random effect is at least a way to say, with little data, how can you try to deal with that? So we're heading that way. It's all a matter of what we can get to converge in a way to be done in several months.
To add to that, we're thinking, one thing I know that we'll talk about regionalization a bit, and there are things, of course, we cannot go into details, but azimuth is going to be a big issue. The waveguide, in the Appalachian. But that's not something we'll look at in NGA-East 1. We have to develop models now. We cannot keep waiting for more data, for more analysis. We're already going beyond with a very strong database that was well processed. So I want to try the regionalization because it's interesting, and we'll try to get it. But it's a trade-off as convergence and choices, and how one remover and one random effect from this can change things. And also one thing that I don't want to go ahead of myself because all these things are all related, but the data set is not really well balanced. We know that. Most of the high quality, higher Nyquist frequencies from Canada, then it's really sparse in the rest of the U.S., which is controlled by the TRA. So Tada will show some slides about that this afternoon. So we need to make sure that if we map differences, they're true differences, or they're not mapped. Now I'm talking about simple things of frequency and content of data, but it could be a source term that happens because of our unevenly sampled data set. So we have to be careful and not over-parameterize and try to fit things that are not really there, and in some ways keeping it to a small number of regions that's manageable is probably the best approach. In the NGA-East 1. We're going to start calling it 1.
So
you said feels better.
This is Ralph Archuleta again. Dave brought up a point that triggered something in my mind. I mean, ignore the stress parameter for a moment, because that could be an independent parameter that's fit in there. But since the duration of the rupture time, the source duration is going to be important, and let's suppose it's independent of the stress parameter for a moment, then what happens is that it really becomes important to have some better idea of, let's say, either a length, let's just call it magnitude area because you're used to doing that. Because now what happens is that how fast that rupture sweeps across a particular length scale is actually going to determine that source duration. And if we're looking at smaller sources for the east, and we use a standard, 0.9 or 0.85 times the shear wave velocity, or God help us if we use super shear if it's got long enough or something like this. But anyhow, the source duration is really a parameter then that gets back to your magnitude area relationship. So if there's a scaling parameter in there and we had the wrong magnitude area, then in fact we could end up with longer durations or shorter durations depending on how it goes.
Yeah, and again, part of the extrapolation at larger magnitude will be done through the finite fault simulation, so these issues are important. Tomorrow afternoon we'll have, Rob is going to address some of the range, what range of magnitude area we should consider and how, because eventually, yes, it's going to reflect not only in the ground motions, but also in the duration that you obtain from the source in terms of finite fault. Yes. Good point.
So I'm worried about the duration model for large magnitudes. That's a piece that bothers me right now in this whole approach and what we're trying to do. If we're doing response spectra, we would just trade it to how do you extrapolate response spectral heights to large magnitudes. So what can we do? Are there other models out there for the duration scaling with magnitude other than 1 over a source duration? Is there anything else that's been looked at? Because that's kind of what we're falling back to right now.
Scale, I'm going to say something that will astonish Ralph, and that is that ultimately it would be really nice if duration and other parameters could at least be correlated with something that's physical. Right? Like Ralph makes the point that ultimately there's the size of the fault and the length of time it takes to go down the fault, and that really is what's controlling the source duration. So even if we haven't determined it that way, it would, that's the question is how and if we can actually relate these empirically derived parameters to something that actually does have a physical meaning, because that's what is really in the end required in order to be able to have some ability to extrapolate them.
Yeah, this is Dave again. I certainly agree with that, but one thing I'd like to point out is the durations that I was showing from the data, if you believe them, are very long for small earthquakes, and presumably that's maybe the physical reason for that is the crust is colder, and so there's less intrinsic attenuation, and so the scattered waves and the coda go on longer, and so on. And I mean, that's the duration we're talking about with the source, with the area and so on, is actually for many of the important earthquakes for the I think for the hazard are going to be more controlled by that aspect of the duration rather than the source duration. And maybe there are certain parameters that people have invented to try to talk about the scale length of heterogeneities and all that kind of stuff that goes into the physics of what's going on. But don't lose sight of the fact that that duration that I was showing is not controlled by the source, and it's very long.
Right. That's also part of the problem with our eastern durations, though, because that's what the information we have on the eastern duration is on the path part of the duration. And it's so overwhelming for every single record we have that we don't really have any meaningful information in the eastern records, any meaningful physical information on source duration. It's all path duration that we're seeing. That's it.
So John Adams had a comment. So I'll ask a favor from the PPRP. Whenever you're asking questions or commenting in the general framework of this workshop, just state your role as a resource expert or proponent expert. You're not acting as the PPRP. That will happen behind closed doors. Okay.
John Adams, Geological Survey of Canada.
Oh, sir.
And in this case, I'm kind of reflecting some comments from my colleague Trevor Allen. And they go back to Norm's original talk. Two things.
You have to talk closer. They won't hear you online.
Norm, that's better. Norm, you talk about hinge points, but you don't really talk about whether you're going to use all of them or one of them or how. And the second question is, when you do your regressions, are there advantages in binning the data so that effectively each bin gets the same weight as opposed to a full regression?
I think, yes, we would consider multiple or alternative breakpoints in the distance, hinge distances, if they are still, let me just say, reasonable in quotes, at short distances, because that's really where the difference starts to apply, and that's something we need to pay attention to. So what was the second part of your question? Oh, the binning. What we try to do, instead of binning it up and saying I want equal contribution and then let the regression go, you can do that. But instead, we're really trying to get a functional form that works. Okay, so that when you check the residuals, you don't find a part that's really off or and so forth. So if we can get residuals that are flat against our parameters, then we've done it. When you try to bin data like that, other stuff gets into the statistical model. Okay, now do I give more weight to those points? No, because you want me to give less weight to them, and other things happen. So my goal would be to do it with an adequate model, as opposed, and not let the regression push you off because you use the simple form that doesn't work very well.
This is Gail. I just to agree with Norm, and to get to his to the residuals point, I find that usually the best way to do that is, or the way that's most effective is, rather than trying to bin at the regression stage, to not bin at the regression stage, but then bin at the stage when you have residuals. And that way you can look at the binned residuals by magnitude and distance and so on, and if there are any bins that aren't satisfactory, then change the form so that it goes away at that point.
Couple of questions, and I'm not speaking as PPRP. Anything you hear from me between now and this afternoon is not as PPRP. First, on that question of the binning, one thing to think about is, because of geometrical factors, you get a lot more data at longer distances than at short distances, and that may be motivating John Adams' question. And so, yeah, ideally you want to fit at all distances, but at least in the EPI work that we did recently, we were forced to downweight some distances for that reason. And with the TA array, that's happening more and more. The other comment I had was actually related to Norm's first presentation. And you talk about having to fit the Fourier amplitude and also standard deviation, so you could get Fourier amplitude squared, which is what you use to compute power, etc. Isn't it easier to simply fit Fourier amplitude squared directly? The only problem is that the coefficients are going to be a little bit strange to you. They look a little different. But on the other hand, you avoid having to assume a distribution shape and whatever else you have to do in going directly that way.
We talked about that, and the problem becomes, what's the distribution, and do we then need most of our regressions are assuming a normal distribution, so a log normal or whatever it's going to be. The Fourier amplitude squared is not, it's different, okay, and so now you could say, well, maybe it's as close to log normal as our amplitude is anyway, right? And so that's a way around it. It's not very hard to track all this stuff, and so we have more experience doing regression on Fourier amplitude than Fourier amplitude squared, so I would like to stay where I'm a little more comfortable, or then jumping to that other part. But we were talking about that last week when we were saying, well, if SMSIM is declaring their spectrum to be a square root of the Fourier amplitude squared, should we be doing that value it seems like it's easier, because then they avoid this whole variance issue and mean versus median. But I think to get this done now, we'll stick with something that we know is approximately log normal. And I don't know, I forget what the distribution was. Nico, you were looking that stuff up in terms of the square of the power. It's got something. So Gabe, not using the microphone, says the Fourier amplitude is exponential for white noise, right? But our data sets tend to be pretty close to log normal when we look at the Fourier amplitude. So when we've done fitting on that before, so Walt, is he still here? Yeah. So in the regressions, when Walt's done the inversion for the response spectra, we're fitting them and looking at the residuals, and they're pretty close, or reasonably close to log normal. So it at least lets it fit into our current engine for doing the regression without going back and setting it up. If you do likelihoods, you can put whatever distribution is in you want, but anything fundamentally different right now is dangerous.
Walt, did you want to comment? No. Okay, thank you. Yes. So, yeah. The one advantage is doing it in FAS. If there's an understanding of what these coefficients are or should be, and there's a physical correspondence that I certainly don't have for this.
The other advantage is it does allow a more parallel structure between the Fourier and the response spectra in the, to the extent that the Fourier spectra of acceleration is kind of parallels the response spectral velocity. So it's easier to kind of cross-check what things are doing.
Any other comments, concerns, questions on the GMP approach from the NGA-East group and Kappa?
More specifically, do you see this as that we're messing up in going this way and really fundamentally missing something by not doing a response spectrum traditional GMPE? We will have some of that stuff with the published models, because these aren't the only ones we're going to consider. But what we've talked about this morning are the new ones that are being generated as part of the peer project. The SHAC evaluation will consider all the other existing models as well. But are we fundamentally missing something?
Ken Campbell, so you mentioned that there's going to be 3 different methods for coming up with Fourier spectra models. And within each of those, I presume there's going to be a whole set of epistemic uncertainties that are calculated, right? So, I mean, you'll have 3 different methods, which is one form of epistemic uncertainty, but within that, you'll do internal epistemic uncertainty, which obviously has to account for all the correlations in the parameters and that sort of thing.
At least in the first approach, we will do that. So there'll be multiple models that come out. I'm not sure of the other 2. If we can get one model out of each of them, I'm going to be happy. I think we don't want to tell them, they got to go make 5 models when there's only time to make 1. But we will capture that piece in the
I was going to say, so as a minimum, these other models, you have to make sure that you're capturing those other models within your models. Okay.
Larry Salamone, Joint Management Committee. Norm raised a good point about the new direction. My general comment is, many times in research, you go down a path and then hit dead ends that can block you or delay you. And considering the commercial need for the product, the short time frame, do you sense that there could be an issue of doing a new approach? And there may be things in the complexities of putting things together at the end and everything, and you might have an issue at the end that would be kind of a show-stopping issue that would prevent success.
Well, that's the answer I gave wrongly to Gabe before.
We've had this discussion between ourselves many times in the last 6 months or a year. I fundamentally believe this is going to be easier to get a robust result out than it is on the response spectrum. It's just a way that we can tie seismology much better into the problem than we can trying to do response spectrum. Trying to model the high-frequency behavior of response spectra is just a nightmare, fundamentally, with kappa in there. And so, for that reason, I have been arguing in this project, we need to go this way because it's easier to get a robust result. Where I'm worried is the duration model. And I can get something out of that from maybe from the numerical simulations. We do have, as Gail was talking about, some basic concept of a source duration. And that's all that we're really talking about. The path duration we have empirically in the East, and you can use that. It's the source duration, and are those different than what we've been assuming or not? Are they really shorter, in the East, and that would be increasing the ground motions and so forth. So I think that's the place. I don't know that it's a showstopper. We can use 1 over the source duration or some multiplier times that is consistent, but I think that's the place that we need to make some progress with. That's where I'm worried about stumbling.
Yeah, I think it's more likely to be among the caveats than a showstopper. So I think it's a caveat rather than a showstopper.
Christine asked if we should talk about kappa, and kappa is not 5 minutes. It's either 0 or hours. So I think kappa we will deal with in October. So, yeah.
We have 5 minutes.